So I hope everyone is fine. These unusual times. Okay, so welcome to the RES meeting. So today we have a set of speakers who are going to talk about hopefully the current and the future of transient science, time domain science, multi-messenger science. It's both science and facilities. So hopefully by the end of the day, we'll have a good overview. So we're going to start with Hood, who's going to give us an overview of multi-messenger science in the next decade. So over to you, Hood.
Thank you very much. So thanks for inviting me. And so I was asked to talk about multi-messenger science in the next decade and the future in general. It's a rather a large topic. So I decided to focus on two specific phenomena. The first is the ultimate multi-messenger event that we are all waiting for, which is the next galactic supernova. And I'm going to ask how we're ready for that. And the answer is actually, to my surprise, no. This is something that I just learned last week for this talk. The second topic I will talk about is a few points on compact binary measures, mostly neutron star measures. So let's start with observing the next galactic core collapse supernova. So the rate of core collapse supernova in our galaxy is roughly 1 in units of academic careers time span. So I guess that many of the participants will see one such event during their career, at least the younger ones. And what you see here is a figure taken from Nakamura, 2016, with different types of emission coming from a supernova, which we are going to observe. So first, before the collapse itself, I'm restricting the discussion to core collapse supernovae. So before the collapse of the core, there is an increase in the flux of the neutrinos from the last stages of silicon burn. There may also be a precursor due to some mass loss events, which we think take place prior to supernova, so we're not sure exactly when and how much and how often. And then once the core is collapsing, most of the gravitational energy is released in the form of neutrinos. So there is about 10 to the 53 ergs of neutrinos radiated. The duration of the radiation is basically the diffusion time of the neutrinos through the core that just collapsed to a proto-neutron star, and roughly after 10 seconds, the flux of neutrinos trying to drop significantly. At the same time, there is gravitational waves which are released. The emission of gravitational waves depends mostly on the asphericity and the rotation of the core. And then we have to wait. We have to wait for the shock to cross the progenitor star. We'll see later how long it takes in different types of supernovae. But once the shock is breaking out, we have what we call the shock breakout flash. And after the shock breakout, there is the entire supernovae, which we all know and love, which continues for, well, we still see 87A. So for many, many years. So let's go over each one of these stages. I will say just a few words and try to focus on whether we are ready or not to observe it in the electromagnetic regime. But I will start with the neutrinos. They are the first to come. So detection of the next galactic supernova is guaranteed. There are about a dozen different detectors which are going to see the next supernovae. And and just Super Kamikanda is going to see thousands of neutrinos. Hyper Kamikanda, which should be operational by the end of the decade, is going to see tens of thousands of supernovae. Neutrinos. And just on the neutrinos themselves, we are going to learn, it will basically make a revolution in the field, redefine what we know about explosion of core collapse supernova. We'll learn about the progenitor. We'll have a measurement of the collapse time just when it happens, the location on the sky, and the distance. I will talk about it more later. We'll learn about neutrino physics, things that we cannot measure now about flavor mix. And if there is a new physics which is we don't know about, there's a good chance we'll be able to detect it. We'll have basically we can see into the physics of the collapse itself and the explosion. We'll see the different stages of the collapse. We'll be able to measure better the neutron star equation of state. We'll be able to measure the radius of the proto-neutron star, the evolution of the proto-neutron star, the cooling of the proto-neutron star, and the formation of the neutron star after the cooling, or if there is a collapse to a black hole, we'll basically see the collapse to a black hole. This is going to be exciting. By the way, in 87A, we saw 19 neutrinos, and I looked at the ADS, there are about 1,000 papers, or about 20 papers, 50 papers per neutrino. And here we're going to see 5,000 or more. Okay. What about alert for multi-messenger detection, basically for gravitational waves and for the electromagnetic detection? So the timing would be roughly 10 milliseconds. You need several detectors. So in one detector it will be about 50 milliseconds, but if we have several detectors, we get about 10 millisecond timing of the collapse itself. The localization is given either by a single detector, which is a super Kamikanda or hyper Kamikanda. In super Kamikanda, it will be 50 degrees square. In hyper Kamikanda, it will be close to 5 degrees square. Using different detectors which are going to be operational in the next decade, Juno and Dune, triangulation will be possible. And then the error circle will be roughly the same as the super Kamikanda, namely 50 to 100 degrees square. We can also get a rough estimate of the distance just by the flux, and we know what we expect for flux from different types of supernova. Now, today, there is, actually for about 20 years, there is a system which is called the Supernova Early Warning System, which is a global system that collects triggers from different facilities. And if there are several triggers simultaneous in time, then it issues an automatic alert. Now, today, this system is working in a way that false alarm rate is expected only 1 per 100 years. Namely, when there is an alarm, it should be an actual event. As I said, the alert is going automatically within minutes, but this is only the timing information. The location is not distributed until there is a human intervention in the circuit. And I think it will take hours before localization will be distributed. Nowadays, there are plans to improve this alarm system in a way that first, it will also issue alarms for low probability events, similar to the way that the LIGO-Virgo collaboration is working now. Second, if there will be a nearby supernovae, there is a chance to see the pre-supernova neutrinos, but this is really nearby. I'm talking about a kiloparsec away with today's facilities. But there will be a pre-supernova alert. Of course, something which is which is very important is to have a fast localization information which is distributed. Now, what about gravitational waves? What about the detection? So there is high uncertainty in the signal of gravitational waves from supernovae. It's not like a mergers where we knew pretty well what we were expecting. But even with this uncertainty, it seems that second generation observatories like Advanced LIGO and Virgo and Kagra will be able to see supernovae if it's not too far away, namely few kiloparsecs, but not the entire galaxy. So a detection is possible, not necessarily take place. Third generation observatory, like the Einstein telescope, are expected to cover the entire galaxies and possibly even satellite galaxies. So I would say that detection of galactic supernovae in gravitational wave is almost guaranteed. Now, as I said, the signal coming from supernova will be a bursting signal. There is no reliable template. And the neutrino signal, which will give the timing, will of course increase the sensitivity. Just a few more things. What can we learn from the gravitational waves? So first of all, we'll see the collapse process. It will be able to, once, if there is of course signal to noise, which is high enough, we'll be able to learn about the core mass, the equation of state of the neutron star, the formation of the black hole, and many more things. We're especially sensitive to asphericity because this is a source of the gravitational waves. For example, if there are jets of different types, we'll be able probably to see them. Different G modes and F modes on the neutron star, transport of rotation, differential rotation, and transport of the angular momentum we'll be able to measure possibly. Even see the SASI, the standing shock, accretion shock instability, which we think that take place during the process. And finally, the gravitational waves and the neutrino signal will measure exactly the same processes. They should be correlated and will provide complementary information about things that we just so far we saw only on computers. What about the electromagnetic radiation? Now, first I would like to focus on the shock breakout and the early emission. So just the first minutes, hours after the shock breakout. Now, one of the nice things about supernovae is that when we look time since the explosion, or actually time since the breakout, we measure, we see farther and farther and deeper into the exploding star. So at first we see only the very outermost layers. For example, during the first hour, we see only the outermost 10 to the 4 solar masses of the envelope, or a wind if there is a strong wind before the explosion. After a day, we look deeper, about 0.01 solar mass. In a week, we see half a solar mass. After a month, we see about 5 solar mass, or basically all of the star. So now, this implies that if we look after a week, there is no sensitivity at all to the outer layer. So we cannot see the 10 to the minus 4 exterior solar masses after a week. So far, when we see supernovae, usually only hours after the explosion, we cannot probe the most external layers. We cannot see, it's difficult to see if there is a pre-explosion mass loss. And in a nearby supernovae, we will be able to see them if we will be able to see the shock breakout and the early emission. We'll be able to measure the radius, the density structure, the outermost layers composition. If there is an asphericity, we'll be able to measure it, even small asphericity. If there is we'll be able to see the nickel mixing to the outermost layers, pre-explosion mass loss, which is very interesting, we'll be able to measure. So altogether, seeing the shock breakout of the next galactic supernova is very interesting, and would like it to do that very much. What about the detectability? So here you have a table with a peak magnitude of different types of supernovae and of the shock breakout and during the peak of the emission. First, what is a time scale? In red supergiant, the shock breakout will take place about a day after the neutrinos. So if we have, say, a few hours delay in the alert, it's not too bad. In case of 97A, like explosion we have, which is blue supergiant, we have several hours, maybe 2 hours before the shock breakout after the neutrino signal. And in the case of a Wolf-Rayet, if it's a 1b or 1c supernova, we have only minutes, something like 100 seconds to see the event. So hopefully we'll have a very quick alert about the fact that we want to see, we need to see this supernova, we want to see a shock breakout. And of course, the peak of the supernova itself is coming after a week, so at least a week. Now, what about the brightness? The brightness is dominated, at least in the optical and IR, and certainly UV, by the extinction. Certainly, if it's a core collapse supernova, we expect to have it in the disk. Work by Adams and work by Nakamura estimated what will be the average, or what is the probability for each for the extinction. And it turns out that for K-band, the extinction is supposed to be something between 2 and 8 magnitudes. In V-band, it's going to be anywhere between 0 and 30, and most likely somewhere between 5 and 26, something like that, magnitudes. So in K-band, the shock breakout, in case of a red supergiant, where the shock breakout is in the near UV, is going to be very bright. Actually, the brightness of the sky during the day in K-band is something like 5 or 6 magnitudes per arc second square. So breakout from a red supergiant will be observable in the K-band during the day. For blue supergiant, it will be somewhere between 5 and 11 magnitudes, and in Wolf-Rayet between 9 and 15. So for all cases, it will be observable in K-band by telescope, at least during the night. What about the V-band? Here there is a huge variance depending on the extinction, but it can be everything between visible easily by the eye to invisible. Basically cannot be seen by the largest telescopes. And finally, an interesting point is that Wolf-Rayet explosions are going to be actually bright in soft gamma rays. So for example, if we look at 2008, which was very bright in X-rays and had a very flat spectrum through the X-rays, up to 10 keV, we're going to see such explosion is going to be so bright in soft gamma rays, say 20 keV, something like that, that it's going to be easily detected by SWIFT, but also by other facilities. So, as I said, the breakout will peak in all supernova will be observable in the near infrared. Saturation is a major issue. If there is a 2 magnitudes event, we can see it only with with basically amateur telescopes. And if we want to get high resolution spectroscopy, it's going to be an issue. It's not going to be trivial. How can we get a high quality spectrum for such a bright event? I don't think that we're ready for that. If there is an alert with a localization of, say, 50 square degrees, we do not have the facilities today that will be able to see it in the infrared. And as you can see, all we need is something which is basically low sensitivity, relatively cheap. In Adams et al. 2013, they give in one of the appendices a specification of such an instrument, which would cost, I don't know, 10,000, few tens of thousands of dollars, not something which is extremely expensive. We need, I don't know, half a dozen such instruments which are distributed around the globe. So every point in the sky is covered at every time of the day. But that's it, and we do not have it today. So my guess, if there is tomorrow a galactic supernovae, we are going to miss the shock breakout, most likely. We'll have difficulty in obtaining early time spectrum, at least in the IR. And if it's a Wolf Rayet, we would like to have alert for Swift, so it will be able to put it within the field of view of the box, which covers about 10% of the sky, but still we need to know which 10% of the sky it is. So we need to have this type of alert within a minute or so. Now we do not have it. So my guess, if there is tomorrow a supernovae, you are going to miss a significant fraction of what you can get in the electromagnetic, especially in the electromagnetic signal. Okay, I have I have three more minutes. That's it?
You do, yeah.
Okay. So let me say only one or two things about neutron star mergers. One thing I want to say is that we're lucky in 1708-17. We're really, really lucky. What you see here is the different peak fluxes of 1708-17, putting it at different distances. In red, you can see everything which is detectable. So optical, the kilonova will be detectable all the way to 200 megaparsec. Gamma rays and X-rays and the afterglows will be detected barely to 100 megaparsec, not farther away. And this is only if the inclination is about 20 degrees, which was inclination of 1708-17. For other types, higher inclination, we are not going to measure even at 40 megaparsec. We're probably not going to see not the gamma rays, not the afterglow, nothing about the jet. Now, here you can see the rates. To have 1708-17, 40 megaparsecs, 20 degrees, one event per 40 to 400 years. We're not going to have another event like that. Okay? At 200 megaparsecs, there will be one event at this inclination per year or something like that. So we're really lucky. Future observation in this field, of binary neutron star will not be as detailed as GW 1708-17, and we need to know that. Okay, let me just finish in one minute. I would put this slide so you can ask me about it. This is a slide about the future progress that we expect in different interesting questions. And my guess, I will just go quickly. We're going to get improved measure of H naught, probably within the next decade. We are going to solve the origin of our process elements, or at least know if it's coming from compact binary merger in this decade. We're getting significant improvement in neutron star equation of state, but probably we're not going to, there's still going to be open questions. We'll also have a lot of improvement in constraining the formation channels of binary neutron stars and BH neutron stars. And about the physics of the relativistic jets, this is going to be a very slow progress. In most events, we'll not see the signatures of the jet. My guess is once LIGO and Virgo will become operational again, we'll probably see one per more than a year, one per every few years. And this is my summary, and I will be happy to answer questions.
Thank you very much. So Niall, do you want to take over for questions?
Yes. Okay. So, yeah, really interesting talk. I think certainly I came away feeling perhaps more optimistic about experiencing galactic supernovae, but a little bit more pessimistic about the rate of progress with the mergers. Anyway, so we've certainly got a couple of questions. So the first one is from Phil Evans. This came through in the chat, and the question is, do you think we know enough about the galactic stellar population that with 100 square degree neutrino localization, one could tell which star, or perhaps narrow down to a small set of stars, that is likely to be the one that is exploding?
You're talking about identifying the progenitor after, or
Yeah.
about?
I think that's the question. Yes.
It depends where it happens. There is a good chance. It depends. Regions which are too crowded will probably be. It will be difficult to identify the progenitor. It also depends a lot about the coverage in IR, and what is the resolution in which we have all the coverage of the galaxy, because with good chances in the optical we cannot see these progenitors. About if the question was about can we guess which one is the one that was actually exploding, only if we saw some very weird activity before. Again, my guess is that not really. There is not a high chance that we'll be able to pinpoint which one is going to explode.
Yeah, it'd be an interesting challenge, wouldn't it? But yeah.
Yeah.
Okay, so the next question you might feel is a bit sort of observer or instrumental centric, but see if you have an opinion. Is it possible to develop neutral density filters to measure the infrared spectrum or imaging with existing instruments? Even a sheet of metal with some holes cut into it that might cut down the brightness so that the supernova would be observable.
I don't know. It's not my field of expertise, but no. I talked with two observers in my department just about that. Basically I learned about this topic just for this meeting during the last week. I didn't know this is going to be such a challenge, and this was roughly the idea that they suggested. And they claim that probably people are going to try and do it within a day or two, once it will be almost too late after the supernova took place. But I don't know if it's going to work or not. I don't understand this stuff. Yeah,
another interesting challenge, as you say. Maybe people would come up with very quick sort of ad hoc solutions if presented with the opportunity.
The problem is that from the psychological point of view, it seems there is not enough incentives to people to invent into it now. Only when it will be too late.
Indeed. Now, we just had another question in, but I think it's more a comment, so I'll read it out from John Morell. The previous question was from Peter Allen. Sorry, I should have stated that. John Morell comments that the probability of identifying the progenitor, etc., also depends on where the supernova is. And I guess this is true for all follow-up. There are fewer telescopes in the northern hemisphere, and the supernova could be behind the sun, in which case the challenges would be much greater if it's,
of course.
Yeah.
Okay, maybe we should move on to Phil. Thank you very much, Ehud.
Thank you.
Thank you to the people asking questions, one of whom was Phil. So start whenever you're ready, Phil.
Yeah, I'm just, I was trying to turn my video camera on, but my participants thing's disappeared. Where is it? There we go. So that you can actually see me looking in the wrong direction. Okay, hopefully you can see my slides. And thanks, Udi, for that introduction and saving me having to talk too much about 170817, which I'm trying to skip over. So I was asked to talk about, what was the title I was given, was actually Swift, Present and Future. And I realized when I gave an updated title to Paul that I missed a trick. So I'm revising from the many facets of Swift transient science to a Swiftmas carol, since we're going to be talking about Swift Present and Swift Future. And I'm sure I can slip the ghost of Swiftmas Past into there somewhere. And I would emphasize that I'm going to give a very high level summary of Swift's contributions at the moment and looking to the future into this transient science, because if I tried to go into detail and everything, we would be here all day on that alone. And I'm representing work done by a lot of people. So a very quick, this is my Ghost of Swiftmas Past thing, a quick introduction to the Neil Gehrels Swift Observatory for those of you not familiar with it. This is Swift over here. Hopefully you can see my mouse moving around. So Swift has 3 instruments. It was originally designed to search for gamma ray bursts. And as such, it has the Burst Alert Telescope, which alerts us to bursts. This is a coded mask. It sees about 1/6 of the sky, 2 steradians in 15 to 350 keV. And then we have focusing X-ray and UV optical telescopes as well. And a couple of key features of Swift here. The BAT is capable of autonomous triggering. So in other words, it does all the work on board itself. It realizes, hey, I've seen some new high energy transient. No, it's not in the catalog. Yes, I should be looking at this. And then it says to the spacecraft, go and look at this. And the spacecraft autonomously checks it's safe and how to get there and slews very, very quickly. So Swift is normally on target with the narrow field instruments within a couple of minutes of the BAT trigger, which is actually pretty revolutionary. So as of this week, I believe this number is correct. Thanks, Kim Page, for giving me this. We've observed 1,415 GRBs that have been detected by the BAT, plus a bunch of other ones detected by other instruments we've followed up. Got redshifts for over 300 of them, which has obviously been historically of great importance and still is going forward. But since this is past, not present or future, I'm going to gloss over that. The other thing, though, to say about Swift is we don't know when a gamma ray burst is going to go off, kind of obviously, and it was built around observing gamma ray bursts. So the whole premise of Swift's operation is tomorrow we are going to observe what we only discovered today. And that necessitates a complete different mentality to your normal observation scheduling for telescopes, especially space telescopes. So we literally plan Swift on a daily basis what it's observing. And this also means this flexibility that's built in means that we are particularly good at doing response to other people's requests, to the extent that so far this year, we have carried out or fulfilled 1,700 target of opportunity requests, which is pretty staggering, I think. And hats off to the guys at the Mission Operations Center for making that happen. So let me just talk about gamma ray bursts for a moment, but mainly looking to the future and a couple of the highlights that I think are going to be important moving forwards. And these are probably subjective, and others may choose to disagree with me about what the key ones are. So let me start with high energy. In itself, this isn't a new result. I mean, EGRET detected some high energy emission way back when. And since Fermi-LAT has been in space, we've been detecting gamma rays from gamma ray bursts, if you like, with Fermi-LAT. But the combination of that with Swift is particularly useful for getting good localizations, either Swift and Fermi trigger independently on the same event, or Swift follows up the Fermi detection and finds an arc-second position in X-rays and maybe in the UV. But there's been a couple of interesting results. This is, I meant to move the caption, sorry, down from my hello et al, never mind. But this is a recent example of a light curve of a joint trigger between the instruments. But one of the key things is that the high energy emission seen by LAT can be long-lived and is generally associated now, it seems, with afterglow rather than with prompt. And this means that we've been able, actually some real breakthroughs just in this last 2 years or so, that HESS and MAGIC telescopes have been able to detect gamma ray bursts in the TeV with, in some cases, quite long-lived emission. And I think this is great news looking forward to CTA as well for the prospects for getting coverage going right up into the very extreme energy bands from gamma ray bursts. Of course, adding neutrinos to that would be awesome as well, but so far we've not got anywhere with that. The other big thing moving forward is something called guano. Now, credit for the development of this must go to Jamie Kenner and Aaron Tohu Vavohu at Penn State University. And Aaron gets away with proposing acronyms that I'm sure I would never get away with, and I'm highly jealous of this. But guano, it's something completely contrived about gamma ray untriggered autonomous notification or something. Essentially, the point is it's a bat dump, hence guano. That is, without going into detail, the bat data are not stored forever because they take up too much space. So they are only 30 minutes of event data normally stored. But what that means is if we realize that something interesting has happened that didn't trigger BAT within 30 minutes, we can dump those BAT data, analyze them on the ground. And again, Jimmy Delaunay at Penn State has been pioneering this, and get an arc minute potentially localization out of BAT, even though we didn't trigger. So I'm showing here a light curve. This is, I think this is the first guano GRB we got an afterglow for. So GBM detected this. Its localization is, many degrees. But with the BAT data dumped through guano, we were able to get an accurate position, or accurate enough position to do a TOO and then find the X-ray afterglow. And in itself, that's hardly the world's most exciting afterglow. But giving you the localization enables us to do other follow-up and potentially probing a different parameter space, such as low luminosity GRBs, but also, if we're lucky, getting triggers on, for example, fast radio bursts, or maybe if we're lucky, an underluminous trigger from a gamma ray burst, from a gravitational wave burst. But for many years now, SWIFT has been much more than the Gamma Ray Burst Observatory, hence the 1,700 TOOs a year. And also that was partly the reason behind its renaming after the Neil Gehrels Swift Observatory in memory of Neil, who was our PI for a long time before his untimely death. So SWIFT does other searches for transits with the narrow field instruments as well. So here's a couple of programs we have going at the moment. The first one is something called S-Cubed. This was led by Jamie Kenner, Malcolm Coe, and myself. So Jamie published a paper on this a couple of years ago, the first one-year paper. We essentially carry out short 60 to 100 second observations in each of these fields of view. You can see up here over a large swath of the SMC pretty much every week, in order both to look for outbursts from known high mass X-ray binders and soft X-ray pulsars in this system, and also to look for new transients. And this has actually been quite a wealth of interesting data. I'm just going to highlight one thing because I think this is really cool because it came out recently. So this is just a light curve of an outburst of a source that appeared. It's got a long SWIFT-J telephone number. It wasn't, I don't believe it was a known source before. We got a very good light curve for it. You see, we hadn't detected it, and then one of our observations, it turned on, and then we've had all these stars, our specific TOO data we had interspersed with our routine once a weekly data. We believe this, and we've got reasonable evidence for the fact that this is a BE white dwarf binary. And if you know your stellar evolution, you'll be thinking, well, that sounds impossible. In other words, this is a clear indication of some pretty funky mass transfer that's been going on in order to create a system with this layout. The other thing that I'll just draw your attention to, and there's a paper by Arash Baramian on arXiv earlier this year, is the Swift Bulge survey, which is a similar kind of program, but surveying the Swift, the galactic bulge, not the Swift bulge. You can see we have this kind of hourglass type pattern that we're observing with that. But looking to the future, of course, multi-messenger is the big thing. And we've already had a good introduction to some of this from Udi. So looking at combining electromagnetic data with other stuff like neutrinos and gravitational waves. And actually this, again, I can bring in the ghost of Swift Must Pass for just a minute, because we've been doing this actually basically pretty much since before the phrase multi-messenger got coined, certainly before it was mainstream. So we've been responding to neutrino detections from IceCube for almost a decade now, and you can see my paper on that. We've been following one from Antares for nearly as long. We actually, even going back again quite a long time, followed up a couple of events from initial LIGO, although they turned out not to be real. And of course, since Advanced LIGO and then Advanced Virgo turned on, everything's gone mad. And here's just a set of papers. If you're bored of listening to me, you can scan in the next 10 minutes or so. But it turns out this is actually rather difficult for various of the challenges. And Udi's reference to this 100 square degree galactic supernova localization is an indication of some of the challenges we have. You know, SWIFT was built with the idea, of course, that when you detect a gamma ray burst with BAT and you slew, you can fit the BAT error region inside the field of view of the narrow field instruments. For reasons that I hope will be obvious, like we can't see the future, we didn't build it thinking about fitting in neutrino or gravitational wave localizations. So we've had to develop new observing capabilities. Again, folks at the Mark and David Palmer at Los Alamos get a hat tip for their work in this. So these are some automated mosaic patterns we can do now, 4, 7, 19. We can actually even do a 37 point with an extra ring around here, but I couldn't find a picture of that in a hurry. So we can search a large area. Of course, there are drawbacks to this, right? If you search a large area trying to find a neutrino counterpart, first of all, it takes longer. It's a bit more of a data analysis challenge, but also you find a lot of stuff. I mean, you can see the little circles that we've got in here, these little green circles, I hope you can see, they just represent the positions of sources that were found. And the problem is if you find a lot of stuff, how do you know which one's the afterglow or the counterpart? Because in X-rays, it's a particular challenge. Of course, the optical sky is incredibly dynamic, but also relatively well known. There is no existing X-ray catalog that goes down to the sort of depth that Swift gets to for us to use as a reference, which is a real challenge. I'll show you a bit more of that in a minute. I mean, yay for Rosito, and the sooner their catalog comes out, the better, frankly. Because gravitational waves just take the challenge to an entirely different ballpark. This is 150914, the very first actual direct detection of gravitational waves. All you need to care about here is that this gravitational wave banana is huge. And it's very difficult to follow that up. So we innovate. And again, this is work that I did with Jamie in particular at the Mock, and David Palmer again, and later Aaron Tohu, just trying to find ways of optimizing the way you can make Swift slew around the sky like a mad thing. And this was an example. This gravitational wave trigger actually was later retracted, but we managed to observe 1,404 different pointings on the sky within 48 hours with the X-ray telescope, which was pretty impressive and shows that we have the potential to do this. But like I say, data mining is a challenge now, because how do you know which source is of interest? How do you pull that out? Is it even possible to know which source is of interest? And I'm going to use the neutrino detection. This should be 22A, sorry, as an example of this. So this was a neutrino that was detected by IceCube on the 22nd of September 2017, while I was at a multi-messenger conference, actually, which is kind of ironic, but also meant that I didn't give this as much attention as I'd like, because I was supposed to be listening to and indeed giving talks. But nonetheless, Swift followed it up. You don't really need to read all this text. The point is we followed it up quickly. We found a lot of sources. One of them is this Blazar, Texas 0506+056. And although we said it's one of the possible sources, we did not say from the Swift data alone this was an outburst. And it was actually the LAT data that confirmed the outburst. And then we looked at it and went, oh, yeah. And this just indicates the challenge I'm going to show you. This is from Azadeh's paper on the object. Just draw your attention to this slide. At the time that we got our first data, when we wrote our circular on this object, this data point here is literally the only thing that we knew about the source, was this data point here. And our data mining system goes back and says, have we or anyone ever seen this before? And in this case, if you look historically, woohoo, Swift has seen this before. And then we say, well, is there anything exceptional about its count rate? And it looks back at its historical levels and says, probably not. Now, with hindsight, you might say, well, look, it had these two sort of lowish points here. It clearly was in an outburst last time we looked. I've got to say, I'm still not convinced. If I look at this light curve blind, I would be strongly persuaded that we're seeing an outburst, but you know, the errors are largish, but maybe, you know, hindsight is a wonderful thing. But this again is just an illustration of the challenge. You know, maybe this one we're lucky to have historical Swift light curve. Often what we've got is a single data point or upper limit from ROSAT, and that is it. And we're trying to infer from that whether our new source is in outburst or is even a new source. Maybe it's just below the RAS limit. And again, eROSITA is going to be fantastic in helping us with that. We continue to follow up gravitational wave events, of course. Neutrinos, of course. And gravitational wave events. Now, this is a slightly old slide, but it's still relevant and shows the point. Gravitational wave localizations are very poor. I mean, detecting the things is difficult enough, right? Never mind localizing them. So this is a simulation I did a few years ago, but basically, if you were to take a typical gravitational wave localization region and search it in descending probability order, how many fields do you have to observe before you get to the right one? And the answer is loads. Now, at least for the more nearby ones within 100 or 200 megaparsecs, you can do better than this, because you can assume that the event goes off in a galaxy, you know about the galaxies, what we know, and so on. And that can help us reduce this curve to this blue one, which is reasonably good in kind of 70% of cases, but still has a massive tail. The ideal scenario is to get a really good position, right? Either because there's a multi-instrument trigger from the gravitational wave system, or we get a simultaneous GRB, although as we've just heard in the previous talk, that's kind of unlikely. But it happened and we were lucky. So this is GW 170817's localization. The blue is the Fermi GBM gamma ray burst location, and the little black here is the gravitational wave position. I find it ironic and amusing that actually in this case, the gravitational wave position was more accurate than the GRB position. I don't know how many people would have predicted that in advance, especially when you only target galaxies. And then there's the famous images that I'm sure you've all seen of the 6 independent discoveries of the afterglow near this galaxy, some X-ray that was found later on, some UV. Swift's results were crucial here, I believe. And again, this was one I think that was passed over briefly by Udi, but the bright ultraviolet emission was actually really intriguing. The lack of X-rays was interesting, although actually the X-ray data were not as constraining as we'd hoped. I'm not really going to go into any of that right now, but the fact that the bright blue kilonova, this is our modeling of the evolution of the blue kilonova from our paper, actually UVOT can produce unique scientific input in this area. And it's caused us to rethink and realize that maybe we should be thinking more about UVOT than XRT as the science driver. In fact, XRT is particularly difficult. This is going to be a challenge to the future because it turned out from the Chandra data, the host galaxy of 1708-17 was in itself X-ray emitting. So this is the Chandra image. I've smoothed it a bit on the left. Here's the host galaxy. Here's the afterglow and a couple of other sources. And if you look at XRT data, this is 50,000 seconds of XRT data, right? Here are the 3 known sources and the afterglow on an XRT image, and you can see they're almost impossible to deconvolve. This is the Chandra image convolved with the XRT PSF, which I basically wrote some new software to try to use an approach of fitting this to the XRT data to try and constrain the brightness of the source, but we never managed to get a detection. And that is only going to get harder because as LIGO and Virgo get more sensitive, although we have the more chance of multi-instrument detections to give us smaller position regions, the average event's going to be further away, and therefore the average angular offset of the actual gravitational wave event from its galactic host is going to go down. So if these things have a habit of occurring in X-ray active galaxies, this is going to be particularly difficult. But it's a challenge that we're working on by, for example, producing new software to do this kind of analysis approach. So just for the last few minutes, moving on to the ghost of Swiftmas future, like Scrooge, of course, we do need to learn the lessons from the past. We need to be aware of the challenges that we've found that we need to face and innovate new ways of overcoming them, which is something we're working on. But we remain active and busy and scientifically prolific. Swift is still detecting GRBs at a high rate. I haven't mentioned soft gamma repeaters, but we detect quite a few of those. In fact, this year, we've detected 3 brand new SGRs. It's been quite an active year for SGRs. There's been 7 triggers in total. We also follow up other people's transients a lot, 1,700 TOOs a year. IceCube seems to have gone mad this last 6 months. It's detected so many neutrinos, and we are following up a lot of these. KM3net, the Northern Hemisphere upgrade to Antares or replacement of Antares, is under construction, and we will be following up their triggers. They're actually better localized than the IceCube triggers. And of course, LIGO Virgo Cagra will be turning on again, hopefully June 2022. So we have a bit of time to get ourselves ready for that. The Vera Rubin Observatory is, of course, a bit of an elephant in the room here. This is going to pump out huge amounts of transients. And actually, there's a lot of work gone on and continuing to go on with Swift, which increases our flexibility of our planning and new user support tools. There is work being done by Jamie to produce new and more efficient methods of proposing large numbers of TOOs so that we can hopefully support transient astronomy coming out of Vera Rubin. And the last thing I want to do is just introduce you to a new project, a newish project which I'm working on, which is our own transient factory for serendipitous transients. So this is a famous event you may or may not have heard of. This is Supernova 2008D. And basically back in 2008, Alicia Soderberg was using Swift to observe Supernova 2007 UY. So these are the X-ray data and UV data of the supernova. And while she was observing this, suddenly this event went off in the field of view completely serendipitously. And this was, I think, the first ever detection of X-rays from the supernova shock breakout, this massive transient that suddenly went off in the field of view. Now, actually, just an aside here, you know, this raises the interesting question, could we do this kind of follow-up for these 100 square degree galactic supernovae that we've just been referred to? The answer is we can search 100 square degrees. It will take a little bit of effort, and we need to know which 100 square degrees. And more to the point, we need to look at the right time. But Swift is definitely capable of searching for a bright X-ray transient in 100 square degree localization. And I'm sure we will do that if we get message from Super K of a galactic supernova. Now, this event is not unique. In a sort of very rough and ready proof of concept, I searched for any other cases like these serendipitous transients. This is one we found. So Swift was observing this object, and a few days later, that object had faded away, but this object had turned on. It turns out just to be a flare star, but it's a proof of concept that we can find transients in Swift data. The problem again is always, most of the time you find an uncatalogued source in Swift data, it's below existing upper limits. So you don't know that it's a new source. It might just be that we're the first person to look at the sky with enough sensitivity. And so I have this ambition, which has been floating around for a long time, because it's kind of tough, to basically build up literally a real-time catalog. So every time Swift carries out an observation, we analyze that in full and add it to a point source catalog, add its upper limits to a catalog. So when we find it, every time we find a new source, we can say, is this a transient? Oh, hang on, Swift looked here last week and didn't see it. Yes, it's a transient. So this process is nearing completion. This is, I'm sure you're desperate to read this, and I've had to rotate it to fit it on the screen, but this is a flowchart of that transient factory. And the stuff in gray is the stuff that's complete. And actually, that's the guts of it. Nearly everything else is just user interface. So I'm hopeful that we'll be able to issue the alerts from this system in some point in the coming year. The real headline, though, I want to end with in my last 7.5 seconds is to emphasize Swift operations remain completely nominal. In actual fact, our functionality in terms of our observing capabilities, our planning capabilities, our user interfaces, our tools to analyze data are still being increased even now. So if our past was productive, the present remains so, and I think the future looks very exciting. So grab hold of the spirit of Swiftmas future and let's go exploring. Thank you.
Okay, thanks, Phil. You certainly kept to time. So I'll hand over to Niall for questions.
Right, okay, so at the moment we just have one, which is, oh, okay, we have question from Joe Lyman. And so what is the timescale from observations to issuing an alert for these Swift transient triggers?
So for a bat trigger, it's essentially instantaneous. For anything that involves human intervention, it's a bit variable. So if we're responding, say, to a guano event, so this is one where we've done our low latency, it needs somebody on the ground to look at it and check that it's real. But we're normally fairly quick. For a lot of the things that we do follow up where we're looking for XRT transients, we issue what we call GCN Counterpart Notices. So those come out essentially as soon as the data are analyzed, which is anything between about 2 and 10 hours after the observations are taken, just depending on the schedule of Swift ground station passes. The beat of the orbit or period means that we don't get to ground station pass every orbit. Typically, I would say about 3 hours. And for the new transient system that I'm putting together, I don't know the timescale yet because at the moment, no transient alerts from that will go automatically because they need some human verification. So the Swift team will be notified within about 10 minutes of the data being on the ground, which again is between 2 and 10 hours after observation. And then there'll be human verification before they're sent out.
Okay, I'm going to ask now one from John Veach, which I think sort of follows up on the last one. So with the new transient alerts you mentioned at the end, would they come with any classification of the object, or does that require further follow-up?
That's a good question. In the initial instance, they're unlikely to come out with classification. I think it will more just be RA deck brightness. I would love if someone can get me or as a student, it would be great to look into some kind of schemes of automatic classifying. Like, you can do X-ray color magnitude diagrams, for example, and see if you can get an approximate classification. In most cases, though, I think it's going to need follow-up spectroscopy or positions. If, like tidal disruption events, it's hard to tell whether we will be, depending on the galaxy it's in, for example, you might be able to tell that the X-ray emission is coming from right at the center of a galaxy, in which case you could flag as a possible TDE. But in a lot of cases, the spatial resolution of Swift compared to the size of the galaxies won't be enough to tell that instantly.
Okay, Rob Fender has just put a comment up. Great stuff, Phil, he says. Just to note that 10,000 serendipitous field variables and transients are present in the Chandra and XMM archives, and maximum likelihood classification of these has been developed.
Yeah, yes, indeed. And so looking into some of that maximum likelihood classification would be something we would do. Of course, our data we don't have the same effective area as them, so our error bars will probably be a little bit bigger. But yes, I fully accept that point.
Okay, next one is from Huri Ziapur. Thanks, Phil. Any plan for long follow-up of short GRBs It is important for finding out if there's any brightening as it happened in 1708-17. I think this is a good question.
Yeah, this is something I know is close to your heart, Neil. Yeah, the answer is yes. We do try to, where we can, keep an eye on short JRBs for longer, or come back to them later on to see if there's brightening. Again, there is still a general challenge that once they get below a certain brightness, we just won't be able to, it becomes impossible unless they're going to get loads brighter. But yes, there is, and this is something that Brad, the Swift PI, is also very aware of.
Good, about time.
We don't do it for all of them, and I suppose we can discuss, and Neil, I'm sure he'd be happy to press for exactly when this follow-up should happen, but we do try to follow the shorts for longer, if that makes sense.
And I guess maybe last question from Paul O'Brien, who should know the answer, but he wants to know, how long will Swift last?
Forever. No, actually, the answer is, that's an interesting question. Swift, as you know, Paul, has no consumables on board. So there are 3 threats to Swift's existence. Well, 4. The first threat is the sun. This is the main thing. So when the solar cycle increases, the Earth's atmosphere inflates, that increases drag on the spacecraft, and the spacecraft starts to deorbit. The latest projections, no one knows what the next solar cycle is going to look like. Current projections have Swift running through to the mid-2030s, though, before its orbit descopes. The second threat is instrument failure, which, you can't legislate for. Who knows? At the moment, all I can say is the instruments are healthy. The third threat is funding failure. That is people deciding to stop funding us. All I can say about that is you should be constantly telling all of your funding agencies, NASA, RZ, and the UKSA, that Swift is the best thing since sliced bread, and you should give us lots and lots of money. And the fourth issue is, of course, space debris. And in actual fact, I believe, we do get warnings from time to time that, there's something getting close to Swift's orbit, and there's nothing we can do because Swift has no rocket propellant. So, when Elon Musk puts 4 zillion Starlink satellites into space, I have no idea what their orbits look like. One just has to hope they're never going to hit Swift. But, all being well, we can keep going for another decade.
Well, that sounds like a good and optimistic note, maybe, to
thanks,
the questioning.
I did know the answer, but I thought it was good.
I know you did. I was only teasing.
We should, of course, note that Swift was 16 just a few weeks ago, and XMM was 21 yesterday. So these missions can last a very long time, which is a good note, which to introduce the next set of speakers who are going to talk about future missions. So first up is Damien, who's going to talk about SVOM.
Can you see my screen?
We can.
Yes, great. I will
Switch to presenter mode, or?
Yep.
That's great. So off you go, Damien.
Okay, thank you. Good morning and or good afternoon, everybody. I'm happy to have the opportunity to talk in this meeting. So today I'm going to talk about on behalf of the SVOM collaboration, and I'll try to give you some pieces of information how we envision in SVOM our contribution to the time domain and multi-messenger astronomy. So I divided my talk into 2 parts. First, it's introductive part to present a bit what SVOM is for people who do not know, are not aware of, and to present a bit the how this mission has been designed for which scientific purposes, what are our observational strategies and data policy. All those aspects are very important to understand how we envision the future and our, let's say, scientific philosophy in SVOM. And in the second part of my talk, I will focus more on the, let's say, target of opportunity programs we have in SVOM, and especially how we plan to face the new decades of alerts and how we hope we'll be able to interact with you guys, with the different scientific communities. So let's start with what is SVOM. So first of all, SVOM is a collaboration of people, mainly Chinese and French collaboration. So you have on top of this slide the emails of the PIs of SVOM, in case I will not be able to answer to your question later. So Professor Zhen Wei at the National Astronomical Observatories of China in Beijing, and Bertrand Cordier at CES Eclair near Paris. And we have also important contribution from Mexico, Germany, and UK Institute, and especially our colleagues of University of Leicester, who are deeply involved in this SWOM mission. So all these institutes form the SWOM collaboration. So now let's go deep into the things. So here's a cartoon of the SWOM satellite. So SWOM means Space-Based Multiband Astronomical Variable Object Monitor, and it is equipped with 4 instruments. And I will start maybe to present the French Eclair instruments. I don't know if you see my mouse here, but on top left of the satellite. So it's a kind of equivalent with the BAT instrument on Swift. It's a coded mask instrument sensitive to the high energy photons from 4 keV to 150 keV, and it's able to localize those photons down to 12 arc minutes. It has a wide field of view, 2 stereo field of view. And this is what we call our trigger camera. So as bad for Swift, Eclair, when it will be able to detect significantly sources, it will trigger automatically an observational sequence on board, which will make the spacecraft slew to align the follow-up instruments to pursue the follow-up observation in different wavelengths. So to complement the spectral range of Eclair, which is comparable to the spectral range of Eclair of BAT, we have installed 3 photoscintillators on the spacecraft, which we call the GRM, the gamma ray burst monitors. So these photoscintillators will extend the spectral range of Eclair up to 5 MeVs. So we will have some overlap between Eclairs and GRM. And of course, these photoscintillators will not be able to localize the sources. They are just here for extend the spectral data of Eclair. So we have also 2 follow-up instruments on board, an X-ray telescopes called the microchannel X-ray telescope. This is where the University of Leicester is, for example, deeply involved. So this is an X-ray telescope, which is sensitive like XRT on Swift to photons from 0.2 keV to 10 keV, with the localization accuracy of the arc minutes around. And compared to XRT, it has a much wider field of view because MXT has a field of view of about 1 degree per 1 degree, so 1 degree square. And finally, we have the visible telescopes, which is an optical telescopes, 40 centimeter telescopes operated with 2 filters, well, broadband filters, what we call the blue channel and the red channel. And its typical sensitivity in the red channel is 22.5 for 300 seconds of exposure. So we hope to launch this beautiful satellite on by mid-2022, for 3 years and 2 more years if everything is okay. I guess when you look at this satellite, you say, oh, it's a kind of Swift. Yes, of course, it's very inspired by previous GRB missions like Swift. It's a kind of combination of Swift instruments and Fermi GBM instrument, but at smaller scales. The overall payload weight is about 450 kilograms, so it's not the same scale than Swift. Okay, so now that was for the space part of SWOM. So we have also, let's go back on ground. So we have also on ground an alert network to communicate actually with the satellite and to retrieve the alert information and all the data. So this alert network is composed of 40 very high frequency radio antennas distributed all over the world. You can see on this Earth map the visibility pattern of each antenna. And with such a system, we expect to retrieve 65% of the alerts within less than 30 seconds at the French Science Center, which is located here in Paris at CEA. We have also a Chinese Science Center here in Beijing at the NAOC. Complementary to this VHF network, we also plan to be connected to the Chinese navigation system, the Beidou network, and also it will help to improve the fastest. It will be the fastest way to communicate with the satellite. So on top of this, we have also developed what we call the SVOM follow-up system on ground, which is actually a network of robotic telescopes that are fully dedicated to the SVOM follow-up activities. So they are a bit slave telescopes, which means that when the satellite is detecting a high energy trigger, those telescopes have the duty to make the optical and near infrared follow-up, photometric follow-up of these sources. So all of our telescopes are completely robotic, and we have from 20 centimeters in diameter telescope up to 1.3 meters for the Colibri telescopes here in Mexico, and for the GFT-1 telescopes here in the Jilin Observatory in China. So we hope that this SVOM follow-up system will be a great added value for the SVOM mission, for improving the optical and near-infrared follow-up of our alerts, but also to participate to any kind of multi-messenger follow-up activities. We also expect to have a partnership with the 2-meter class telescopes in China. And also we should have guaranteed time on the Las Cumbres Observatory network. So this SVOM follow-up system is still, it's still open to everyone to participate, to inject a telescope inside, and it's still under construction actually. Okay, about the observational strategy of the satellites on board, it's kind of different than Swift, I guess. So as I said, the satellite will be launched, I guess, we hope, in June 2022 from China. It will be placed in the low Earth orbit at 600 kilometers with an inclination of about 30 degrees. And the originality of the SVOM pointing strategy, that what we call the B1 attitude law, is that our pointing strategy is nearly anti-solar. So the main drawback of this is that we cross the Earth half of the time of one orbit. So each the one orbit is about 95 minutes. So every, let's say, 45 minutes, we will cross the Earth in our field of view. So which reduce a lot the duty cycle of our narrow field of view instruments, the MXT and the VT telescopes on board. To about 50% and to about 65% for the Eclair, which has a very wide field of view to steradians. So why we did this choice? First, as I said before, Eclair is the trigger instrument, and compared to BAT, who, you could correct me, Phil, but is going to trigger at like 10 keV or 15 keV, we will try to trigger at 4 keV with Eclair, which means that we are very sensitive to X-ray sources and X-ray background. So our main goal for this pointing strategy was to avoid as much as possible the galactic plane, where you have a lot of X-ray sources that could disturb our trigger algorithm. And this is what you can see on this Eclair exposure map for 1 year of mission. So all the red parts here are the part where we spend much more time, and all the blue parts are the part of the galactic plane where we don't spend so much time. We will spend some time on galactic plane, but very few compared to the high galactic latitudes. And the second point of this nearly anti-solar pointing is that so we will have the sun on the back of the satellite. So most of our high energy triggers will be detected during night side, which means that we want to maximize the photometric and spectroscopic follow-up of our SVOM alerts on ground with large telescope, but also any kind of robotic telescope who would like to follow up our alerts. And this we do this to optimize and to have a very quick response of the facilities on ground to make very early follow-up of our alerts, instead of having maybe half of our alerts close to the sun and they are lost. And we will detect about, so this mission has been designed mainly for gamma ray burst detection, and we will detect about 60 to 70 GRB per year. So I come now to the different scientific programs we have in SVOM. So as you can imagine, the SVOM satellite and all the SVOM mission has been designed to detect and perform the follow-up, multi-wavelength follow-up observation of gamma ray bursts. This is really the core program of the mission, the gamma ray burst. and especially we would like to improve the coverage at a very early time in the optical and infrared wavelength, and to also have both photo redshift estimation of our GRBs, because we can localize them very quickly. And thanks to our nearly anti-solar strategy, we hope to have a fast spectroscopic follow-up, and also to be able to constrain the spectral energy distribution of the prompt emission up to 5 MeVs, just with one mission instead of cross-matching Fermi GBM and Swift together, for example. We also have a target of opportunity program, which deals with all known GRB transient sources. This is the program that is dedicated to tackle the problematics of the multi-messenger astronomy, gravitational wave follow-up, neutrino follow-up, but any kind of transient that could be interesting to follow up on, actually, with our instruments. And finally, we have what we call the general program, which is SVOM will be actually an open observatory, and we will give some observation time to people who will wish to use our instruments in a call of proposal each semester, and the time will be awarded by a TAC. I will not talk much about the general program because it's not maybe the main program that will be used for the transient sky studies. I will come back to this different time devoted to different programs for the mission later. So a core program devoted to GRB, a target of opportunity program, and a general program to tackle different astrophysical subjects. A quick word on the SVOM data policy, very quick about the core program. So the GRB detection and follow-up. Our wish is to give to deliver in real time all the scientific products that are downloaded from the VHF network, that are under the supervision of the burst advocates, and we will try to make them as soon as we have them in our scientific centers available for everyone. It's very similar to the Swift or Fermi GM procedure for the alert. And all the scientific products will be, for a given GRB, will be public 6 months after the data production. For the target of opportunity program, this is not set in stone. We have a general philosophy and we have some ideas, but this is not completely set in stone. So this is still under discussions. But the idea is that for TOs that is triggered by a SVOM COI, so we will make publicly available as soon as we have those scientific products, a fraction of the scientific products that are relevant to perform follow-up observation by external teams, which means that we are going to provide the position of the sources we are going to detect, the flux at the detection time, maybe an estimation of the fading rate or things like that. And we will make it available as soon as possible. But the number of products that will be publicly released will be addressed case by case, different depending on the source of interest we are following up. For TOs triggered by non-SVOM COI, so external scientists, all the scientific products here will be publicly available as soon as they are available. Of course, the raw data are always a property of the SVOM COIs, and for the general program, it's a kind of standard procedure. We will have a semester for a call for a proposal. Each proposal should have in association, be in association with the SVOM COI, and all the SVOM data will be distributed to the responsible COI, and we will guarantee 1 year of proprietary period before all the scientific products become public. All right, at this stage of this presentation, let me give you some takeaway messages, maybe very obvious, but I think they are representative of what we think in SVOM and what we think is now the reality of the observations for people who want to study the transient universe, what we need actually. And we need, first of all, of course, multi-band instruments to have global pictures of the physics of the phenomena we are going to study. This is clearly the legacy of Swift with the study of GRBs, but with many other kind of sources, of course. And also the multi-messenger campaign we have done so far the past years. So this will be our philosophy too. We have a large set of multi-band instruments in SVOM, and we will use for this purpose. We must have also a worldwide network of telescopes. It's important now to have a worldwide network of telescopes, but with different sensitivities and field of view characteristics. For example, for gravitational wave follow-up, you cannot rely only on 8-meter telescopes to perform the follow-up. They will not do it before you detect actually the source, which is the right one, or at least a very promising one. And we need also, of course, synergies and coordination between space and ground observatories. And this will be the SVOM observational strategy, of course. And this is also the strategy of many SWIFT, also on Fermi and many other facilities now in space. And we must have as much as possible wide field of view instruments in all bands. This is what we try to have in SVOM. So the Eclair and GRM instruments are really, on gamma rays are two stereo instruments. MXT X-ray telescope is quite wide field of view telescopes, 1 degree square. And we have also very wide field of view optical instruments on ground with the GWAC 500 square degrees, and also 4 square degrees for the GWAC F30 telescopes at the Xinglong Observatory. And finally, we must have very responsive network of facilities, which means that now for a satellite platform which studies the Trondheim sky, having a TO program is something unavoidable. You need to have this. And as much as possible, we need to have dedicated follow-up telescopes on ground to perform the follow-up observation of different alerts, both for SVOM alerts, but also for multi-messenger alerts. And last point is that we should provide our detection follow-up observational results as soon as possible to everybody. I mean, not necessarily all the scientific products, but the scientific products that allows external people to perform follow-up of their sources, and to have a better scientific return on the different follow-up campaigns. And this will be our philosophy for the next decade. And I have now a couple of slides to focus more on the TO programs of SVOM that will be at we hope, the service of the time domain and multi-messenger astronomy needs. What you have to know first is that in SVOM we will have 3 kind of target of opportunity programs. Not all of them will be accessible to everybody. I mean, by accessible, not all of them can be triggered by everybody. So we have 2 programs that can be only triggered by SVOM COIs in case of multi-messenger alerts, so gravitational wave, neutrinos, etc. alerts. We will be able to perform at the beginning of the first year of the mission 1 target of opportunity for multi-messenger alert per week. For this TO, we will allocate between 1 and 14 orbits of time to spend on these sources. 14 orbits corresponds to 1 mission day, about 1 mission day. We hope to be pretty fast with the system, the alert network we have in hand, and to have a maximum latency between the time you take the decision to make the follow-up observation, the TO, and the time where you have the first observations, the first data. We hope to have no more than 2 hours using our S-band radio antenna station. And if we use the Beidou system, the Chinese system, we hope to go down to 4 hours of latency between the TO decision taking and the first observation. Of course, this TO will use all the power of SVOM, the different instruments we have in hand, both on board and on ground. We will have also what we call exceptional target of opportunity. For example, it could be the galactic supernova, of course, will be an exceptional TO. We expect to have this kind of exceptional TO 1 per month, to be able to make this 1 per month. And about the allocated time, maximum latency, and the instruments that will be used for this TO, is roughly the same than for the multi-messenger TO, try to be as fast as we can, and to perform long exposure or to spend long time on these sources. And finally, we will have target of opportunity that we call nominal, that will be triggerable to everybody. Everybody could trigger this kind of TO. We will deliver 1 of such a TO per day at the beginning of the mission with 1 orbit. So 1 orbit is 45 minutes of exposure, because we have 45 Earth occultation during one orbit. The typical latency will be between 1 day or 2 days. So you are not going to deal with the same constraint than for multi-messenger alerts or for an exceptional alert. It's a bit different, but you could use any kind of instrumental form. The difference between, as I said before, a TO triggered by its form COIS is that only a fraction of the scientific products will be available publicly. But those scientific products will be key products for you external teams to perform follow-up observation by your own without having any needs for or any help from us. All the scientific products will be publicly available if the TO is triggered by external people also. All right, so this slide is just to show you a bit. It's not an exhaustive list, of course, but on which kind of sources our TO programs could apply. Of course, in the transient sky, we have a large diversity of sources, of time scales, of luminosity scales, on different physics. So this is just here an example of which kind of TO program we could use for. And we think that it is important to have different response and observational strategy according to the different types of sources you will have. For example, you don't need to be super fast. Well, it seems that we need to be quite fast for the shock breakout for the galactic supernova, but not that fast. For example, for supernova TO. For gamma ray bursts, we think to use, for example, TO, nominal TO to make revisits of bright GRBs. This is something we will set in place for the revisit follow-up of GRBs. Okay, so as I said, now I come back to the time devoted to the different programs and especially to the target of opportunity program in SWOM. So at the beginning, the first years of the mission, we will deliver 15% of the mission time to the target of opportunity with a maximum rate of 1 TO per day. So these are this famous nominal TO. And we expect to, of course, increase the mission time to the TO because in SWOM we think that TO programs are very important for such a kind of mission like us or like Swift or like Fermi or etc. for any kind of satellites which have capabilities of fast slowing and be able to make a different pointing per orbit. So in the extended mission, we hope to be able to provide 40% of the mission time to the TO programs and to go to a maximum rate of 5 TOs per day. Last point I wanted to talk about is about the infrastructures around the target of opportunity program. At the system level, it's a very, very complex things to set. And at the beginning, we had maybe naive thoughts about how we might handle all these kind of things within SWOM. The idea was that we had to listen all the alert channels we could have from optical infrared alerts for gravitational wave alerts, from gamma ray, X-ray alerts like Swift, Fermi alerts, from neutrino ice cube, CAM3net, Antares, radio when SCA will be there. So we realized that it will be probably a real nightmare to handle this, and we won't have the manpower to develop the tools to digest all this multi-stream of alerts, to process all this stream of alerts, and to perform filtering of alerts, and then to ingest everything in a TO manager to make the priority for the observation and to scale the observation for the satellite. So either we make a trade-off, like we reduce our scientific perspective and we just choose few of them, or we ask for people who have expertise and manpower to develop, to handle all these millions or hundreds of alerts per night, which we are not able to do this. So we now rather think to do this for the TO infrastructure. This is something we are still thinking about, and it's not set in stone also. But we have the chance that the Vera Rubin Observatory, the LSST project, will will provide us millions of alerts per night, so which is a nightmare. But in parallel, they ask people to develop a new generation of brokers to be able to handle all these kind of alerts per night and multi alert. So for us, these guys, so the new generation of brokers that are in competition for being a broker, official brokers of the Vera Rubin Observatory, are the very important tool we could have in hand to at least digest all the multi-stream of alerts, millions of alerts per night, for example, for LSST, several alerts per day for gravitational waves, several alerts per day for gamma ray burst or gamma ray triggers, etc. To process those alerts and also to perform the filtering system of these alerts. So in France, we have the Think new generation of brokers, and in the UK, you have also the LISER broker that both are in competition for being selected by the LSST collaboration. And the ideas we have in SVOM is to develop scientific modules inside those brokers to at least perform the filtering system of the multi-stream of alerts. And then we retrieve only one stream of alert, which is completely filtered, that fits our scientific needs, of course, what we want. And then it is easy for us to, ingest this in our TO manager tools inside our science center. So we proceed in two steps, one step in the new generation of brokers and another second step in our science center to schedule the observations. So I will finish on this second takeaway bunch of messages, which is what we think is now important to have in terms of dedicated programs and infrastructure to study the transient sky in the next decade. Of course, we need now real-time coordinated activities. We need customized target of opportunity programs to fit the different observation needs of the different alert types. We need to be connected now in real time to the worldwide multi-messenger community. I think it's a need. And we need to be very responsive in the decision taking and the scheduling of the observation of such TOs. And we have to also make the very basic observational results publicly available as soon as they are produced to allow people, external teams, external groups to perform follow-up observation as soon as possible. And about the infrastructure, we emphasize the fact of the importance now of the new generation of brokers that are initially devoted to handle the Vera Rubin Observatory transients. We emphasize their importance because they have the technology now to easily deal with millions of alerts per night, to provide services to quickly filter the alert streams to your scientific needs. They provide efficient astro classification tasks with deep machine learning. They provide cross-matching tools. They can cross-match also different stream of alerts together to if you want to cross-match, for example, Swift and GW alert very quickly. You could do this. So this is very important, and you also have in your collaboration, in your mission, a smooth organization of the TO system, because it's a very complex system at the system level. And finally, synergies between the different scientific communities are very crucial for high scientific impact. So we really emphasize the fact that we need to collaborate each other. And thank you. I can answer to your question.
Okay, thank you very much, Damien. So we have time maybe for one or two questions. Oh.
Okay. Don't have at the moment are any questions. I had maybe one or two just sort of technical questions. One is you mentioned the figure of 65% for the number of alerts that are received by the Science Center within 30 seconds of the onboard trigger. I guess I'm wondering, if one were to ask how many will be received within 5 minutes or 10 minutes, does that fraction increase to nearly 100%?
I can't answer you very accurately. I guess it's increasing a lot within minutes, of course. But the problem of this thing is that we have some holes, for example, in the Pacific Ocean, which means that for someone else who here you will have to wait a few minutes, I think, few tens of minutes for the maximum if you are in the worst configuration. If you are crossing the South Atlantic anomaly, you will also have some delays. But I guess, yes, within few minutes, the number increase at least close to 90%, but I can't say precisely this number.
No, okay, that's sort of what I was.
As I said, we're also planning, sorry, to use the Beidou system. So if we manage to be connected on this, it may solve this problem actually.
Yes, yes, okay. Right, any other questions for Damien? Doesn't look like it. So
I stopped sharing.
Yeah, and you know, we obviously, I should say, we could, in principle, people could still ask questions to individual speakers using the Q&A afterwards, providing the speakers keep an eye on that Q&A box just to see if anything has been sent for them to answer.
Yeah, okay, so thank you very much again, Damien. So we'll switch to another mission that's soon to be launched. That is Einstein Pro from YMN. You there, Wyman?
Yes, can you see me, Paul?
I can see you, yeah. So we can see the
slides. Can you see my screen?
Yeah.
I hope it works this time.
Let's see. Yeah, that looks good.
Okay, good.
So go ahead.
Okay. I would like to thank the organizers for the invitation. It's a pleasure for me to introduce the Einstein Probe mission. So, you know, the X-ray sky is rich in high-energy transients, and many bright and interesting ones have been continuously discovered and studied. And currently, there are two monitoring missions operating mainly in the X-ray band. The MAXI mission, working into 30 kV band, scans the whole sky almost every 90 minutes. And Swift BAT monitors a substantial fraction of the sky in the 15 to 150 keV. And in 2 years' time, we're going to have Swarm operating, which is similar to Swift. And their wide field instruments all made use of either slit camera or the coded mask aperture, which do not involve focusing of X-rays. So for the next generation of the all-sky monitor in X-rays, we really need some kind of focusing instruments to increase the sensibility of the monitoring, which means that we should look deeper of the universe. And at the meantime, we should keep the large field of view. And now we have already this technology to do this. This is the so-called lobster eye micropole optics. So this is the imaging principle for lobster's eyes to see the world around, but in the optical band. So this is an ideal optics for X-ray all-sky monitor. So it can provide a very large field of view and a better angular resolution, which can be as good as several arc-minute, and also higher sensitivity compared to the non-focusing instruments. And the focusing efficiency is optimized in the soft X-ray band. As this technology has been studied by various groups all around the world for many years, and a number of mission concepts have been already proposed. And we have started to develop the MPO technology about 10 years ago. And here in the middle, what you can see is the X-ray image we obtained using our Lobster Eye MPO telescope achieved at our lab, which has an angular resolution of less than 5 arc-minute. So we were just lucky enough to have our mission concept selected by our agency as the first of this kind. Okay, so what is the Einstein probe mission? So Einstein probe, or EP in short, is a space X-ray observatory for all sky monitoring to find and to characterize high energy transients and to monitor source variability. So it's a mission of the Chinese Academy of Sciences, and it was proposed in late 2012, and it was formally adopted in December 2017. Now we are in phase C, and the launch date is planned at the end of 2022. The lifetime is for 3 years, nominal, and we hope to have a goal of 5 years' time. And the Einstein probe is also an international collaboration project. So we now have 2 partners. One is ESA. ESA participated into the mission by the Mission of Opportunity, and also MPE in Germany. We're also in discussion with CNES to extend the collaboration to with French colleagues. The payloads of the Einstein probe mission. So there are 2 kinds of payloads. The first is the wide field X-ray telescopes, we call WST. There are 12 modules of this. So they are based on this Lobster eye micropole optics. On the focal sphere or focal plane, we use CMOS detectors. Okay, so it's going to have a very large field of view. It's 3,600 square degree field of view, which is roughly 1.1 steradian. It will work in the soft X-ray band from 0.5 to 4 keV. It has got an effective area of about 3 square centimeter, around 1 keV. It's quite small. It appears to be small, but actually this is the same effective area for almost all the directions within the field of view. It has a resolution of about 5 arc-minute full width half maximum. And this can give us a very good source allocation accuracy down to less than 1 arc-minute. In addition to WST, we have a follow-up X-ray telescope. We called it FXT. There are 2 modules of FXT. So they are just the conventional water one type X-ray optics. We're going to use CCD on the focal plane. It's a small field of view instrument with 1 degree field of view. It's a normal X-ray telescope working from 0.3 to 10 keV band. And the effective area, so for each of the mirror modules, the effective area is 300 square centimeter at 1 keV. Now we have got two of them. The spatial resolution is 30 arc seconds, half power diameter. So the spacecraft is can do the autonomous X-ray follow-up observations. So we have the onboard data processing to search for transients in real time. And once a transient is discovered, the spacecraft will slew and point the follow-up X-ray telescopes to target the source and to do follow-up observations automatically. And then at the meantime, we can also send the alert information quickly down via two means. One is the VHF network, and another is the Chinese beta system. And also there is an uplink capability to do TOO, actually very quick TOO observations. So this diagram shows the grasp of the WST. So the grasp is actually the effective area times the field of view. It's a measure of the monitoring capability. So on this diagram, I show the EP-WST graphs as the black line, and also I show the compared to the Rosetta and other missions graphs. As you can see that the EP-WST has huge graphs, almost 1 order of magnitude higher than the Rosetta and other missions. Of course, here I only plot the X-ray focusing instruments. So about the mission profile, so the satellite will be put on an near Earth circular orbit of 600 kilometers, which is 96 minutes in orbit period with an inclination of 29 degrees. There are basically 3 observation modes. The basic mode is to the survey. So we're going to use 3 snapshots per orbit, looking at the night sky, okay, to avoid the sun. And each pointing lasts for about 20 minutes or so. And once a transient is discovered, we're going to have this autonomous X-ray follow-up observations. And the spacecraft slew time from point to another point usually takes 3 to 5 minutes. The third is the TO observations, so we can have TO observations. And as I said, once a transient is discovered, so the alert data will be downlinked very quickly. We're going to use Payload system, the Chinese satellite navigation system, to download the short messages of the alert data. Meanwhile, I know we're also discussing with CNES to make use of the French VHF network, which has been developed for the SPOR mission to extend the downlink rate. The alert information of the transients will be made public immediately after the taken. And for the quick TOO observations, we can uplink the TOO observation command very quickly using the Chinese Payload system. We hope to do it within a time latency of 10 minutes or so. Okay, so here I show you the WST survey monitoring footprints in one day, the simulation. So basically, in 3 orbits, the WST can cover most of the night sky, but this observation mode can be disrupted once a transient is discovered. Then the satellite will enter the follow-up observation mode, or if there is TO observations happened, then TO observations will be carried out. So in half a year time, we will cover the whole sky. Okay. And this also provides a very good synergy with the multi-wavelength and the multi-messenger facilities like AST, SKA, SWIFT, SWARM, LIGO, and so on. Okay. Okay, here I compare the sensitivity of EPWST to the other missions, wide field monitoring missions. So you can see here's MAXI, here's SWARM and the SWIFT band. And in the soft X-ray band is the Einstein probe WST. And there is more than 1 order of magnitude increase of the sensitivity for the Einstein probe. So there is a huge discovery space. The magnitudes, limiting magnitudes I plot here is for the sensitivity after data accumulation for 1 day. Here I already take into account the survey mode for the EPWST. Okay, so the main science goals of the mission. So first, we will carry out a systematic survey of soft X-ray transients and the variability of X-ray sources at an unprecedented combination of high sensitivity and high cadence. Particularly, we are interested in discovering the otherwise quiescent black holes at almost all astrophysical mass scales and other compact objects by capturing their transient X-ray flares. Okay, for massive black holes, this means tidal disruption events. And we hope to detect and to localize the electromagnetic wave sources of gravitational wave events by synergy with gravitational wave detectors. Since when we propose the mission, since black holes and the gravitational waves are the predictions of the general theory of Einstein's relativity, so we named the mission after this great scientist. Okay, here I show you some science capabilities of the mission. I would like to first discuss the tidal disruption events. So tidal disruption events have been predicted and discovered in recent years. So just when a star is approaching a massive star, can be totally disrupted by the black hole. The timescales for the peaks, it can last for from days to weeks, and then start to fade on timescale of months to years. So TDEs, they are a unique probe of otherwise quiescent massive black holes in normal galaxies. Some expected results out of the observations of EP. So we're going to obtain a large flux limited sample of X-ray TDEs at a discovery rate of something like 100 per year. So this allows us to study the demography of TDE. And currently the X-ray TDE is the order of 20 or 30 or so. And also we expect to detect some TDEs at the early phase or rising phase, which allow us to do a more detailed study of the physics inside. And also the TDE will be sampled with X-ray light curves and the spectrum. Here I show a simulated redshift distribution for a TDE sample after 1 year data taking. So TDEs are a lab of a complete cycle of black hole accretion. So we can use TDEs to explore the accretion physics and also to study the formation of relativistic jets and to explore the low mass end of black hole population and the growth once we if we can discover the intermediate mass black holes. And also there are papers claiming that the binary massive black holes can show them up in light curves of TDE, like a recent paper published just a few weeks ago. Here I show you an example of a detection of a nearby TDE. Actually, this TDE happens in massive black holes, actually intermediate mass black holes with a mass of only 10 to the 4 solar masses, but it's quite nearby. So it can be detected easily with Einstein probe WST. And also WST can catch the rising phase, as you can see from the light curve of WST, and can keep monitoring the light curves up to several months' time. And from one pointed observations by the FST of only 3 kiloseconds, so we can get a proper spectrum for the early phase. So another major science goals is to detect the X-rays from gravitational wave events. So so once we receive an alert from a gravitational wave detector, so we'll do a very quick TOO observations by sending commands uplink within 10 minutes after receiving the GW alert. First, we will point the WST to the GW source locus, and for 1 orbit or 2. So using the large field of view, we can cover almost the entire locus of the GW sources for 1 or 2 orbits. And after that, we're going to use FST to do a sequence of snapshots to target the galaxies within the locus and also within the distance range. And each observation will last for 5 minutes or so. So if there are any potential or promising targets discovered, we're going to do deep follow-up X-ray observations with XT for those promising candidates. So this is basically the strategy we're going to take to search for X-rays from gravitational events. Actually, in particular, we are particularly interested in detecting any unbeamed X-ray emission, possibly produced following the neutron star merger, in addition to the short GRB signal. There are some models recently predicted that if a merger product is magnetar, there may be X-ray emissions produced, which is almost isotropic and behave like an X-ray transient on timescales of, say, hundreds or thousands of seconds. So there are also tentative suggestions that such transients could have been found, like those found in the Chandra deep fields. They called XT2 or XT1. Because the X-ray emission is unbeamed, there is no need that the short GRB, the GRB jet has to be pointed towards the observer. So we estimated that such X-ray transient could be detectable with EPWST within LIGO horizon, and EP should be able to test such kind of models. An interesting thing is the fast X-ray transients. Okay, for GRBs, so we expect that the GRB, the hard X-ray and the gamma ray signals will be provided by synergy with other GRB missions like Swift, Swarm, or Gcn, which was launched 2 days ago. So particularly with EP, we are interested in detecting the X-ray rich GRBs or low luminosity GRBs, which we predict to be detectable about 10 per year, and also short GRBs at the same rate. The high rush GRBs, of course, is very interesting, and we predict that they can be detected at redshifts of 10 or even beyond. I believe Lorenzo will talk about this in his thesis talk, so I'm going to skip this here. So supernova shock breakouts will be very interesting to detect. So they're going to probe the supernova physics and also the progenitor stars. And so far, only a few candidates known in X-ray. So with Einstein probe, we predict that we may detect about 10 per year also, but this is highly uncertain because we know very little about the rate of supernova shock breakout. So we're also keen to detect the X-ray counterparts of FRBs. So the nature of FRBs remain unclear until recently with this discovery of the galactic magnetar in an outburst state as the counterpart of one FRBs. So we simulated that such kind of events can also be detected by EPWST, okay, provided that the FRB happened inside our galaxy. So this is the simulated X-ray image and also light curve by WST. So the last one is UAX. We expect that UAX and X-ray binaries in nearby galaxies can be detected by WST in a survey. So this is the simulated image of one UAX discovered by XM Newton some years ago. And then this is the image of the data stacking for 1 month's time and the simulated the light curve. Okay, there is a wide range of other science topics that Einstein probe can explore, which I won't have the time to discuss. So I will go to the summary. So the future of monitoring the transient X-ray sky is bright, enabled by Lobster Eye MPO technology. So the Einstein probe will be a unique and a powerful mission in this field in the years to come. And the synergy with multi-wavelength and the multi-messenger facilities offers a great science opportunity. And we also need follow-up observations by ground-based telescopes across the electromagnetic and the magnetic wave bands. We look forward to the collaborations in the future. And thank you for your attention.
Thank you very much, Wyman, and thank you for keeping to time. And thank you for letting us know about the launch. I hadn't somehow picked up on that a couple of days ago. It's very exciting. So,
yes.
Right, okay, so we have a number of questions already in. So the first one is from Gavin Lamb. He says that Maxi is finding around about 3 times as many X-ray rich GRBs as would be expected from a simple extrapolation of higher energy GRB rates. Have you factored these objects into the Einstein probe detection rates, and would EP follow-up of these events help localize and classify them as GRB-like transients or something else?
It's a very good question. We haven't thought about this. Of course, we're going to do synergy with Maxi as well. So we're going to definitely to do follow-up observations of X-ray transients discovered by Maxi to localize them. And but we haven't got an estimation of these kind of things. So I will do a study, a homework, and I hope that we can give you an answer later.
Okay, next question from Paul Quinn. Looks like a promising observatory. Is there a mechanism in place to do prompt follow-up of exceptional transients with Chinese optical and radio facilities?
Yes, we are coordinating the ground-based optical and radio telescopes in China, as well as other facilities in other countries, because we don't have large telescopes in China, and what we need is a network of optical and radio telescopes all around the world. So this is indeed something that we have to work out in the next 2 years, and we actually encourage international collaborations on this issue.
Okay, thank you. Next question from Susanna Vergani. And this is something I think I've discussed with you before, but how many very high redshift long GRBs do you expect to detect per year?
This is a very difficult question. We have done simulations, but we're not very confident in our results. So from basic, very simple calculations, we found that we might detect GRBs with redshifts beyond 7 or 8. We may detect something like around 6 or 7 per year. For GRBs beyond redshift of 10, we may detect about 3 or so. But this is highly uncertain, and for EP, it would be very difficult to identify them. How do you know they are high redshift? They are high redshift GRBs. So this will be the strength of Thesis. It's got an infrared telescope which can do a proper onboard follow-up in the infrared. So this is something that we also would like to collaborate with large telescopes in the world. About
yes.
3 or so, I think.
Yes, indeed. Yes, a tricky but potentially good problem to solve. In fact, there are a number of questions coming in. If we've still got time, Paul.
Yeah, you've got a couple of minutes.
Okay, so next question from David Buckley. Is this the first mission to use Lobster eye optics for an X-ray mission? And what is the improvement in detection efficiency? So perhaps you'd just point to your previous figures on that, sort of give an indication, don't they?
Okay, I am not sure whether maybe this helps. I'm not very sure. Yes, indeed, the detection efficiency. I'm not very sure what that means. Do you mean the technical or the operational? From technical point of view, we are very much concerned with the contamination of the mirror. And also we would like to make the aluminum coating of the MPO plates and also CMOS as thin as possible to make the efficiency higher. And it's really challenging, I have to say, yes, as the first try of this kind of optics in space. There are a number of difficulties to deal with. Yeah, we're trying our best. This is what I can say.
Okay, so another question from Huri, which is an interesting one, and Let's see what you make of it. Any plan for background mapping in soft X-rays, for instance, for cross-correlating with stochastic gravitational waves? So I guess that's kind of all sky,
right.
large area mapping.
To be honest, I haven't thought about this, but I think maybe the other missions like Rosetta could be in a better position than EPH to do this. Yes, we will produce an all-sky map, and actually we have a simulation I have no time to show. Yes, indeed, but I think perhaps a more interesting thing is to do the imaging spectroscopic for the diffuse emissions in our galaxy. Yeah, for your questions, we will think about that.
Yeah, it's an interesting one, certainly. And finally, then, last question from Susanna again. Are real-time alerts being made public?
Oh, yes. All the alerts from Transcend will be made public immediately, once verified by our burst advocates.
Excellent. Okay, thank you.
Okay, thank you.
Okay, thanks very much. Just to comment on David's question about lobster eye optics, of course, FOM is also using lobster eye optics, but in a narrow field of view. But having two missions launching in the same year will be exciting.
Okay.
And Bepi Colombo, of course, is already on its way to Mercury with micropore optics,
Yeah.
so at least we know they survived launch. Okay, so we'll move on to the final talk this morning, which is a future mission, Thesis, that Wyman mentioned, and Lorenzo is going to tell us about it.
Yes, good morning to everybody. I'm sharing my screen right now. So, okay. Okay, I think you can see my presentation. So thank you very much to Paul and colleagues for giving me the opportunity of talking about Thesis at this nice meeting. And of course, Paul himself, Neil and several Julian and colleagues here are also highly involved in this mission. You will find more details with respect to what I'm just summarizing right now on the Thesis website. You find here the address, and in these two main papers on advances in space research. But more papers are coming on the archive in the very next days. So Thesis is a transit energy explorer and the universe surveyor. Is a mission mostly aimed at eventually exploiting the high potentialities of long gamma ray burst for investigating the early universe, as well as full exploiting short gamma ray burst and possible other transients for multi-messenger astrophysics, and more in general to provide a fundamental contribution to the study of the transit energy sky, and very strong synergies with next generation very large facilities that are being developed through the whole electromagnetic domain. So let's say ELT, TMT in the optical, SK in the radio, CTA, Athena, and as well as gravitational wave and neutrino detectors. So allowing these facilities in which many countries are investing a lot of effort and money to fully exploit their scientific capabilities. So Thesis was proposed to ESA in response to the call for the next M5 mission, so a medium-sized mission in the framework of the Cosmic Vision program of ESA, by a large European consortium coordinated with myself as a proposal on behalf of INAF of Italy, with, of course, main roles of University of Leicester, with Paul coordinating, and Diego Goth for France, Eclair, Sant'Angelo University of Tübingen, and Enrico Bozzo University of Geneva, as well as a further contribution by the countries you see here, so Spain, Poland, Denmark, Belgium, Czech Republic, Slovenia, Ireland, and also direct contribution by ESA to the payload. So eventually Thesis was selected in 2018 with, together with Spica and Envision. So I think you are aware of these two other mission concepts that are, as well as Thesis, were undergoing a phase A study for, as candidates. you may also know that now Spica is no more in the process. Spica was to be a large mission with a significant contribution by Japan. It was a mid-infrared large observatory. Envision instead is a mission to Venus. So this is the overall schedule of the M5 process. So we are now in the last phase of the phase A study. Mission selection review is just coming on next spring, and final selection by the ESA Space Program Committee will be in June. And then, if everything goes fine and Thesis gets selected, it will be launched in 2032. So in this time frame, where also Athena, for instance, will be launched there, we will have a ELT, TMT likely, and possibly next generation gravitational wave observatory, for instance. So getting to the science case, first main topic of this year's science case is, as I mentioned, full exploiting the long gamma ray burst for investigating the early universe, which means exploiting the properties in the X and gamma rays of this event that makes them visible up to the very early universe, redshift of 9 or even more, thanks to the huge luminosity, as well as the fact that they are produced in the core collapse of very massive stars, which die when they perform. So in principle, the star-star formation rate, evolution, they may be the electromagnetic sign of the death of a POP3 star, or they may trace the environment of POP3 stars. They provide us clues on the early galaxies and on cosmic ionization. So to be more clear, we can see here on the left the near-infrared counterpart of the higher redshift gamma ray burst, redshift of 9.2, this fading light that is following the gamma ray burst proper. And for instance, if we manage to detect a statistical sample of gamma ray burst, high redshift gamma ray burst at redshift higher than 6, so in the first billion years of the universe, we can provide a substantial contribution to the determination of the star formation rate evolution as a function of redshift. On the right, you find a quite now aged plot on what was the situation a few years ago, but still there is a large uncertainty on how the star formation rate evolution that is assessed well up to redshift of 6 or 7 extrapolates to very high redshift. And this is, of course, fundamental also for understanding if for stars were actually the main source of cosmic ionization, and in general, to understand the forced population of stars. So even more impressive is this collection of images taken by the Hubble Space Telescope pointing at the direction of 6 very redshift gamma ray bursts after this fading light completely disappeared. So you see that even the Hubble Space Telescope, a large facility in space, cannot see anything or almost anything. So we know that in these directions, there are 6 high redshift galaxies. We know that they exist, where they are, at what redshift they are, simply because we were capable of catching this counterpart before it faded away, do an absorption spectroscopy, and estimate the redshift. So this means that gamma ray bursts are a unique tool to unveil the population of very high redshift, low luminosity and low mass galaxies. Even if this will improve a lot in the future with JWST, still these next generation observatories will sample the brightest, or will miss the weakest and low faint end population of very redshift galaxies. Moreover, of these galaxies that are invisible, that are below the detection threshold of the large telescopes, not only we know that they exist, where they are and what redshift they are, how many there are, but through absorption spectroscopy on this slide before it fades away, we can also, of this invisible galaxy, learn a lot on their metallicity, the neutral hydrogen fraction, and even the properties of the intergalactic medium. So this is really a breakthrough in early universe cosmology that is clear to cosmologists, but the main issue now is that despite the efforts of many observatories in space, so Swift, Fermi, Conus Wind, and then robotic telescopes on the ground, very large telescopes on the ground, we are still stuck with 7 gamma ray bursts at redshift higher than 6, as can be seen here, in the last 20 years, so from the beginning, if you want, even more than 20 years. So the main aim of Thesis is putting here several tens in a gamma ray burst in a few years of operation. And of course, if the mission can live as much as, not as swift, but something more than the nominal 3 years of operation, this will be really a substantial revolution in high-redshift gamma ray burst. On the other hand, a mission that is capable of doing this kind of breakthrough in high-redshift gamma ray burst will also provide a substantial contribution to the more general time domain astrophysics, because it will be capable of covering the soft X-ray sky with possible extension up to the soft gamma rays with a unique combination of large field of view and source location accuracy and sensitivity, as I will show in a while, thus providing a substantial contribution to time domain astronomy, but also by detecting electromagnetic counterpart, detecting localizing and possibly characterizing the electromagnetic counterpart of gravitational wave signals or neutrino sources. It will provide a fundamental contribution to multi-messenger astrophysics. Just to give you an idea on multi-messenger astrophysics, this is, all of us know very well, the nice picture that emerged in 2017 with the first detection of gravitational wave signal from neutron-star merger by LIGO, and the detection of a short gamma ray burst in a coincidence, in a temporal coincidence, and from a region consistent with the gravitational wave error region, which was a confirmation of a conjecture that was put forward since several years, that neutron-star merger system produce gravitational waves and produce short gamma ray burst. So the relevance of short gamma ray burst for multi-messenger astrophysics was demonstrated. And also there was the discovery of this near-infrared emission, the kilonova emission produced by radioactive decay of very heavy elements being formed by the neutron-rich material during and right after the merger process. And all this nice, beautiful observational picture required the contribution of many observatories, again, space, on the ground, many hours or days. And Thesis aims at doing all of this, at least for a fraction of these events, by itself. So in principle, Thesis is capable to detect and localize accurately, few Arc minutes, the short gamma ray burst, possibly detect and localize the possible soft X-ray emission here on the bottom right that is expected by some models if after the merger there is a supramassive fastly spinning neutron star left, and further refining the position by detecting and localizing the kilonova emission in the infrared or the near infrared afterglow of the burst. So really a breakthrough contribution. How it will be possible to achieve such ambitious goals? This is thanks to a mission concept that is in the mind of the worldwide community on gamma ray burst, multi-messenger astrophysics, time domain astronomy. So in Europe, in the USA, in Japan, in China, everywhere in the world, the dream of this community is to put together a mission that puts together a monitoring of the sky, of the high energy sky, which goes from soft, very soft X-rays, which with a leap in sensitivity with respect to current detectors, an extension up to gamma rays, and an automatic follow-up on board with a near-infrared telescope. And this is the concept of Thesis. There are similar concepts being studied by other communities in the USA, in Japan, as we know. But in Europe, with Thesis, with the phase A study by ESA, is for sure ahead and is having the lead in this direction. So the payload of Thesis will include a soft X-ray imager, which is based on the same technology and concept as the Einstein probe mission, that the wide field monitor of the Einstein probe mission that we just heard about. It will be made of 2 SXA Lobster eye cameras. So again, micropore optics in Lobster eye configuration with CMOS as detectors that will cover a total field of view of half a steradian with the location accuracy better than 2 arc minutes and better than 1 arc minute for many sources. And so providing an impressive combination, as we just heard for Einstein probe, of wide field of view and sensitivity. So just to give you an idea, when we think about focusing X-rays, we think a large field of view is 1 to a few degrees is already a huge field of view. Here we are We are talking about focusing soft X-rays over more than 1,000 square degrees in the sky. At the same time, while the SXI will provide us with the requested leap in sensitivity for high redshift gamma ray burst, at the same time, if we want to detect and localize and characterize any kind of gamma ray burst, so also short hard gamma ray burst for multimedia astrophysics, ultra long gamma ray burst, which may be also an indicator of pop-3 stars, under luminous gamma ray burst, X-ray flashes, and more in general, provide the contribution to the general time domain astronomy multimedia astrophysics that we expect. We need to flank the soft X-ray imager, the Lobster cameras, with a proper GRB monitor, which is in our case the X gamma rays imaging spectrometer, which is made of 2 coded mask cameras. So coded mask, similar technology to SwiftBat, for instance, or Eclair on boson, but the different technology here is in the detectors, because by coupling silicon drift detectors with crystal scintillator, we are capable of covering simultaneously energy band as large as from 2 keV up to 10 MeV. So with location accuracy better than 15 arc minutes, up to 150 keV, thanks to the coded mask. So of course the concept is that any gamma ray burst or transit of interest that is triggered, so identified, localized by one or both of the monitors, of course the joint operation of the monitor will improve the significance of the detection, because for instance low threshold detection by one instrument may be reinforced by a detection by the other instrument. So this is much more than the sum of the 2 instruments. Will command a slew, or request a slew of the spacecraft, which in a few minutes, in a way similar to what Swift is doing, but also SVOM will do, will point, but in this case, a near-infrared telescope to the direction of the gamma ray burst, a near-infrared telescope which is covering the wavelength wavelength range of the near-infrared from 0.7 to 1.8 micron with a large field of view, 15 per 15 arc minutes, and 5 filters. So here I give some more details, but I think this is not needed. This is simply showing on the top the principles, how this Lobster configuration optics work. So don't go into detail. Of course, we need to know that the point spread function is a cross arm here, depending on the number of reflections that the source X-rays occur in these pores. And this is these are current or almost updated design during phase A of SXI cameras, and these are on the right, of course, the number of pixel sizes and so on. Just remark that we proposed CCD as detectors, X-ray CCDs, but then with ESA preferred us to develop CMOS detectors. So, of course, I remark that this technology, we have University of Leicester as a worldwide leading for many years. So this is really the occasion for fully exploiting eventually this big heritage of University of Leicester and UK in this technology, as also we heard from the comments by Paul before. This is instead a sketch, this is more than a sketch, this is a mechanical assembly design of an XGS camera with the main properties. So here on the top right, we see of course, the principle of working of these silicon drift detectors coupled to crystal scintillators. This is a technology which is being carried on by Italy in a combination of INAF, INFN, and the university, so Italian National Institute for Astrophysics and for Nuclear Physics in several years. So here the message is that we are building or studying a detector which will have more than 1,000 square centimeter effective area above 150 keV, where there is no mask, and when there is below the mask we have 500 square centimeter down to 2 keV. So this is really the novel. We cover an energy band from 2 keV up to 10 MeV with this instrument. It is true that there are other instruments, including the Eclairs on SVOM, will get back down to 5 keV, but here we're talking about hundreds of square centimeter down to 2 keV. If you want to compare to the Fermi GBM, which is some tens of 100 square centimeter, but with very, very poor effective area at 10 keV, for instance. And this is for the IRT. On the left, you see the design of the current design of the telescope, and on the bottom of the camera, the telescope is provided directly by ESA, European Space Agency, whereas the camera is the responsibility of the French colleagues. The overall instrument is responsibility of our French colleagues. And as you see, as I mentioned, this is working in the near infrared with 5 filters, I, Z, Y, J, and H. And these are the sensitivity with the goals. And of course, the location accuracy will be of the order of the arc-second. It will work with imaging and spectroscopic mode. So the spectroscopic mode will be granted through GRISM within a subsection of this large field of view, so 2 per 2 arc minutes, with a resolving power of 400. The course configuration was proposed by ESA. During the proposal, we actually had proposed a Cassegrain configuration, but this is for improving the accommodation of the payload on the spacecraft and allowing a larger field of view at the same time. This is just to mention the evolution of the design during the phase A study, which, as I mentioned, started in the fall of 2018, and now it is in its final phase. It will end in next spring. So this is on the top left, the configuration we proposed: 3 XGIS cameras, 4 SXI cameras in a line. Then, for accommodation issues and better observation efficiency of the mission, this was a bit reshuffled. Now we have 2 larger XGIS cameras, so no miss of scientific performances, and different location, so different shape of the field of view. There were also studied and evaluated the first budget of the mission. Here on the right, you see a kind of pictorial based on the CAD model from the first analysis by ESA. Here you see the budget. We're talking about a mission that will go into a low Earth orbit, more or less 600 kilometers, less than a few degrees inclination. This is to keep the background, especially in the XGIS, as low and as stable as possible. This is based on a lot of experience with missions like BeppoSAX, Agile, and so on. We can compare the background variation on the Fermi GBM, for instance, with Agile or BeppoSAX. So, and you can actually see how much the inclination of the orbit makes it difficult for, and the background varying a lot, for instance, for the GBM. And this is very important if we want to improve much our detection capability, especially for low significance events like the ones associated to nearby gravitational wave signals. This is a further evolution of the mission concept during the consolidation review, which was the last very important milestone of the mission on this spring, 2020. So now we have 2 SXI cameras for improving the accommodation and the programmatic and technical feasibility, but we have an increased duration of the mission from 3 to 4 years. So now the nominal duration is 4 years. Of course, there will be a possible extension up to 2 years, but of course this will depend on the result. So there is no technical limit to the duration of the mission. It can also last 10 years, for instance, or more. This is very important when we talk about 4 years, because this is the nominal funded duration of the mission by ESA. There are no technical issues, and an extension of at least 2 years is already considered by ESA. And this is the mission operation concept. So you see on the left, of course, it is resembles those of SWIFT, of course. The pointing strategies you can see on the top right will be to have a pointing of the IRT, and so also the other instrument, the optical axis of the SXI and the GIS, which are the same as the IRT, more or less, to point in a 60 degrees inclination with respect to the ecliptic pole. And this will allow us to have a distribution in declinations that you see here in this picture of the detected gamma ray burst by Thesis, then localized, which is centered at low declination, so to favor the follow-up from ground telescope. As we said, the synergies with ground large facility of the future are very important for them, for Thesis, but also for them. And of course, as I mentioned, triggers and location by the module will command the slew of the spacecraft, and there will be several observational modes with the IRT aimed at detecting the counterpart, the internet counterpart, measuring the redshift, which is the main task of very main task of the mission on high redshift gamma ray burst, detect and localize and measure the redshift of very high redshift gamma ray burst. And then, of course, a lot of more science. But once the redshift is measured, the first task is done, and then possible characterization of the source is done through observation in spectroscopy mode or further imaging, depending on the flux of the source. And of course, all the information on the trigger location, redshift, and so on is promptly transmitted to ground through a trigger broadcasting system. So this is the combination of these instruments and this mission profile, which give to TCUs the capability, as I mentioned, to detect and localize any class of gamma ray burst. So this can be shown in this simulation where I show the classical spectral peak energy, peak flux plane, which means spectral hardness and brightness of the gamma ray burst. So here on the left, you see the bulk of the population of high redshift gamma ray burst and very high redshift that is currently, for instance, uncovered by a mission like Fermi GPM, but this is true also for Swift and so on. So from the point of view of detection, the monitors, the combination of the monitors will be able to detect and localize accurately any class of gamma ray burst, from the very high redshift to the short ones, to ultra long, underluminous, and so on. And for a good fraction of them, TCUs will also be capable of detecting and localizing the infrared counterpart, which means localizing the burst at a few arc seconds or even better, and measure the redshift. So really a complete mission for gamma ray burst and for their use for cosmology, multi-messenger astrophysics, and even fundamental physics. These are just snapshots on the performances. So you see on the left, the comparison in terms of luminosity versus redshift, here on the top left. The red points are what is achieved up to now, and the violet points are what will be achieved by TCU. So going much deeper in luminosity and much higher in redshift. And here on the bottom left, you can see a comparison between the red line, which is the TCU's annual rate of detection of gamma ray burst as a function of redshift, compared to the blue line, which is the infrared, of course, capability of Swift. And you can see there is really a huge leap. This is actually, I think, one of the main figures showing the advancement of TCUs with respect to Swift or the current era. And on the right, you see these capabilities put in the cosmological context, where you see the red points are the gamma ray burst with current identified with current redshift, and the yellow points are the TCUs gamma ray burst that will be detected and localized and with measured redshift, because otherwise there would be many more. Those are the ones with measured redshift on board in only 3.5 years of scientific operation, because nominal duration of 4 years means more or less 3.5 years, as I mentioned. It's a mission that may last many, many years. And this is to be compared with the red points, which are coming from more than 20 years of effort from many worldwide facilities. And this is simulations on how we can use this gamma ray burst for early universe cosmology. So you take this star formation rate evolution as a function of redshift. You can see there's still large uncertainty at redshift higher than 6, 7, or 8, despite here, this is taking into account the recent measurements of very redshift galaxies through the Hubble frontier field, for instance. But as I mentioned, this is still true that these facilities are sampling only the brightest parts of the top of the iceberg of the distribution of very redshift galaxies. Instead, TCUs, through the unique capability of gamma ray burst of detecting telling us that there exist where they are very redshift galaxies, even if they're invisible to these large facilities, could improve, as you can see in these orange dots, compared to the, for instance, red dot, which is what we can achieve up to now with a few gamma ray bursts at very redshift. So it will be really a strong improvement in the accuracy of the measurement of star formation rate evolution. And then on the right, you see the same for metallicity through DLAs, AGN and GRB DLAs, the blue and gray point, and the green and red points are the one from TCUs. And these are simulation by our experts, including Neil in this audience, but many more of them, of course. And this is on the bottom left, an estimate on how with Thesis we could, the accuracy in which we could estimate the cutoff magnitude in the luminosity function of redshift galaxies. On the right, in this plot showing in the x-axis the escape fraction of primordial galaxies with respect to ultraviolet photons density, you can see these contours can be obtained by Thesis with tens of gamma bursts larger than 6, and these are of course parameters fundamental for actually assessing if these photons from primordial stars can actually explain cosmic ionization. On the aspect on time domain and multidimensional astrophysics, on the left, bottom left, here you see the impressive grasp. This is a kind of still a qualitative plot, but this is the impressive grasp of Thesis compared to, for instance, Rosita or XMM. So this is comparing to other focusing X-ray optics. So this is just, of course, Thesis is a monitor, XMM Newton is not, but it's to give you the idea of how a small effective area instrument, like a Lobster eye camera, as has been shown also for Einstein probe, thanks to its huge field of view, can provide an efficiency in the survey, a survey speed, which is really impressive. And in the right, you see the sensitivities in red and black of the SXI and the G is a function of exposure time, with reported the fluxes and the time range of many classes of sources. This represents how many classes of transients could be detected, localized, and characterized by Thesis, not only in the X-ray and gamma ray, but also through possible follow-up with the infrared telescope. If we focus on multi-messenger astrophysics, on the top left you see the timeline of Thesis compared to the timeline of the next generation gravitational wave detector, updated second generation, upgraded, and that is here on the top, on the blue, and possible next generation telescope like Einstein probe or Cosmic Explorer. So in principle, the timeline of Thesis could also, especially if extended, overlap with these very large facilities. On the bottom right, you see the capability of Thesis of detecting and localizing gamma ray burst, short gamma ray burst of the same type of the gamma ray burst 170817, which was the only one electromagnetic counterpart of gravitational wave signal for neutron star to star merger. So thanks to this shows the redshift up to which redshift or distance Thesis could arrive as a function of the viewing angle. So the message is not only we have a gamma ray burst detector and monitor, SXI plus XGS, which especially the XGS has a much larger area with respect to the GBM. So if we compare to the GBM, because it was the GBM to detect such a short gamma ray burst, so the GBM was a low significance, so it was a significant detection, but of course a weak event, soft event. Here we have a detector which is many times larger in the effective area with respect to the GBM, and with an energy range that goes down to 2 keV, and with SXI down to 0.3 keV. So this means that we will be much more sensitive in absolute in the energy band of the GBM, but also we extend to much off-axis, more off-axis events. So this is, of course, will improve with respect to the current situation of the GBM, but a lot the number of similar gamma ray bursts, short gamma rays that could be detected. Or, if you wish, also extend the horizon to these events. So again, I remark what I already mentioned, the capability of Thesis through short gamma ray burst, possible soft X-ray emission, to localize and detect the localized counterparts of gravitational wave signals down to few minutes. But if we also exploit the follow-up with the IRT, either through the afterglow or through the kilonova, here this is the kilonova again of 170817 compared to the sensitivity limits of the Thesis IRT. You can see that it can be very well detectable, such an event. We can localize down to 1 arcsecond these events. These are a simple example on how one can exploit the joint electromagnetic and gravitational wave measurements of these sources. Of course, there are many simulations on the use of this combined observation for cosmology, for assessing the cosmological parameters, and because, of course, you have from the gravitational wave signal the distance, which is somewhat more cosmologically independent. It is dependent on the model that you use for the source and for the gravitational wave signal, but it's independent cosmology. On the other hand, you have the electromagnetic counterpart, which gives you the redshift. So you have the redshift, a model cosmology independent measure of the distance, and of course, this is what you dream to have, and you call a standard candle of siren.
We have 2 minutes, Lorenzo.
How many? Sorry, Paul.
2.
Okay. I'm concluding, right, with showing additional capability, of course, for the study of gamma ray burst itself. This is straightforward. We have missions that will provide hundreds of detection and characterization of gamma ray burst at any redshift through this huge energy band with excellent spectral and timing capabilities, timing down to a few microseconds, about 2 keV. And these are examples comparing on the left a spectrum of the Fermi GPM with a spectrum of Thesis. You can see how, and we know very well, colleagues working on gamma ray burst prompt emission, how is important the low energy part of the spectrum for assessing different models of the prompt emission, which is still one of the main open issues in gamma ray burst science. And on the right, the possibility of detecting kind of absorption features which are very, very relevant to understanding the circumburst environment and thus the projector, and even measure the redshift. And this picture summarizes, of course, the strong synergy of Thesis, for instance, for cosmology, with the large facility of the future already mentioned, with Thesis providing detection, localization, and redshift of very redshift gamma ray bursts, which are then followed by Athena, for instance, in the X-rays, by ELT, TMT, and so on from the ground. I remark that this kind of science is also in the main science of these facilities, which need a facility like Thesis. On the other hand, these facilities will complement a lot and provide a lot of additional value to the scientific return of Thesis, and this is true also for multi-messenger astrophysics. So I conclude just mentioning that in addition to this, in a way somewhat similar to SWIFT, as SWIFT was designed as a gamma ray burst mission, but then it became more and more important as a flexible observatory, a general purpose X-ray observatory, despite the XRT. The telescope is small compared to Chandra or XMM, much more small, as well as the IRT on board Thesis will be a small telescope compared to large telescope. And the same, we will have a guest observer program allowing the community to use Thesis as a general purpose observatory. So in summary, I conclude, again, Thesis is really, from the point of view of the European community, but in general for the worldwide community, is a unique occasion now that it is this very final stage of competition and selection with ESA. We have the real possibility of having this mission, finalizing all the efforts of this worldwide community, especially the European community, but not only, on technology, on science, on gamma ray burst cosmology, gamma ray burst in general, multi-messenger astrophysics, and time domain astrophysics. And of course, again, the synergies are very, very important, and grant that this mission will involve the astrophysical and cosmology community at large, of course. So I conclude, there will be in spring 2021, in March, a Thesis conference, main conference that was to be held in Malaga, in Spain, but it will be difficult given the uncertain situation with the COVID-19 disease. So it may go virtual. You will be reached by updates on this by email. And please visit our website or contact us if any of you would like to contribute or get more information on Thesis. Thank you very much. I'm fine. I'm finished. Thank you, Paul.
Okay, thank you, Lorenzo. So we are running into the lunch break, so perhaps we'll delay questions, if it's okay, till the end of the afternoon session, just to allow people, because we need to start on time so we can finish on time. So if that's all right with everyone. So Julian is chairing this afternoon. We will start again at 1:45 UK or 2:45 European, whatever that time is in your time zone, with Sheila Run. So we'll see you then. We'll leave the Zoom link going, so you won't have to reconnect if you wish. If you want to, I'm sure you can. So we'll see you in a little while.
Okay, bye.
Bye.
Surface of the Earth, marking positions in space-time, gravitational wave signals coming in from the cosmos change the relative position of those inertial markers, and we sense that using laser interferometry, essentially large-scale laser interferometers, and so that is our measurement technique. Excuse me, and currently there's operating a network of these observatories around the world. So just to remind you of what the status of the current network has been over the past few years and a bit of a forward look. We have, of course, the two LIGO observatories in the US, one located in Hanford, the other in Livingston, and they turned on in 2015. Before that, again, operating and continuing to operate is Geo 600, which is a smaller instrument located in Germany. The UK has specific partner interests in both Geo and LIGO, again with contributions to both. We work in partnership together with the Advanced Virgo Observatory, again an international observatory but located in Italy, but again with several European partners, again operating that jointly. CAGNA in Japan is another observatory which is just operating, and I'll talk a little bit more about how that is fitting into the detector network. And there is, of course, planned for operation in India, essentially a third LIGO-like instrument, advanced LIGO-like instrument. And the current sort of vision for that is that it would turn on in actually quite an advanced configuration. I'll say a little bit more about that in about 2027. So that's the global network and the sort of timings compared to where we are just now. And as a quick reminder, this again is the current picture of the observing runs that the network has carried out or will do in future. Looking a bit forward, you'll see a reference at the bottom there to the observing scenario paper that describes this in much more detail. I've basically given you the punchline on what those observing runs look like. It's modified slightly, again, from what's in that paper, because of course COVID has had its impact in many ways, and one of them is on this observing schedule. So 04 and 05, the runs in the out years, again, are modified slightly from what's in that document, again. But to just remind you, the sort of first detection, of course, happened back 2015, announced 2016 in the first observing run with LIGO, again, binary black holes. Of course, 02 saw Virgo join the network. That was a phenomenally successful run in 02. Having Virgo there was exceedingly important to deliver the science. Again, the reason we need that global network is for multiple reasons, but it's science driven. It's partly to give us the directional capability, of course, to tell where gravitational wave signals are coming from. So having Virgo there was extremely important. Multiple detections in that run, of course, including the first binary neutron star merger detected. And again, we heard about some of the science again associated with that and the joint working with Electromagnetic and other partners to deliver the science from that. And there were, multiple, if we're talking about transient astronomy, there were multiple events detected in those two observing runs, to the point where in 2017, the field published its first transient catalogue. And this is the sort of pictorial summary of how the gravitational wave compact binary coalescences detected in those runs sort of looked, again, sitting in context with the knowledge that we had about existing black holes from electromagnetic observations and isolated neutron stars. And you can see, again, it's a snap. There's of course many papers devoted to all the science of this. This is just the headline pictures. Of course, the binary black hole systems, some of them overlap in mass with the existing black holes whose existence is inferred from astronomy. but once you get to the merged systems in particular, they're creeping up in mass. And of course, again, we heard already about some of the fantastic science done by a whole variety of astronomical collaborations associated with that binary neutron star detection. But for the field to get to this point of publishing a transient catalogue in a couple of years, it's particularly exciting, again, given in advance the uncertainties about exactly what our rates would be. So to bring us up to date, we are here, of course, at the end of 2020, and that has encompassed a third observing run with the LIGO, advanced LIGO and Virgo instruments at improved sensitivity, and there was some detector improvements between the O2 and O3 runs. The spacing out of these runs is deliberate so that there can be detector improvements in the intervening time when the observatories turned on. They were not turned on at their full capability. So between O2 and O3, there were a variety of instrumental improvements. And the numbers you see here are for binary neutron range for binary neutron stars. The observing scenario contains the sort of intended planned range. We can compare that to the actual detector range. Again, it's I think also in the publication there, where for Hanford, the sort of median, again, the range fluctuates slightly through a run as the detector operating conditions change slightly. For Hanford, the median range was about 108 megaparsecs. For Livingston, 135, so pretty much as intended. For Virgo, again, 45, very close to what was intended, and Cagra, again, just tentatively starting to operate there. That run also, again, exceedingly successful. We are still in discovery space in the field, I think it's fair to say. So that observing run was split in two. The results and a catalogue paper are recently out from the first half of that second catalogue paper. I'll only pick out a couple of highlights, where, one of which was, again, in terms of mass, of course, detecting even heavier mass black hole mergers, again, into the intermediate mass black hole range, which is particularly exciting. There are a whole range of individual papers for individual events from this run, but this is the catalogue paper that brings all of that together. Again, just to give you a feel for that, there were sort of 39 candidate events, and I think in about 26 weeks of data, so 1.5 per week. So that sensitivity improvement that occurred made a significant difference, and we'll see that in a bit in terms of the rates. And that's an important point. This is now the sort of up-to-date picture of the detected systems in terms of their masses and types. They're without this time the electromagnetic picture on in the background there. And as I mentioned, up towards the top, you can see again, I think it was GW 1905-21 again, which resulted in both, actually, I think, of the original progenitor masses were pretty heavy, but then getting in well into the intermediate mass range for the resultant black hole formed, again with all the implications that come with that around what that means for black hole formation. So very exciting to be at this point. Just to sort of highlight why we do stop and make detector improvements, you can see the plot here, which is the cumulative number of events or candidate events for the first, second and third observing runs, and you'll see that sharp knee between O2 and O3, and that is directly coming from the improvement in sensitivity that came from the instrumental changes. Because I think there's often a temptation when we're making detections and exciting events are coming in to just to leave the detectors on, leave them running. And there is a trade-off between leaving them running and making them more sensitive. but I think this is fairly convincing in terms of why it's important sometimes to stop, spend the time, improve the detector sensitivity here. The addition of squeezed light, some higher laser power, and some changes of the optics, and it made a significant difference in terms of that. Both, again, two things: event rate, and of course the other thing we care about is the size of the individual events and the precision with which we can measure parameters. So there really are strong science drivers for detector improvements and improvements in sensitivity. And so following on from that, as we look forward a bit for the next 5 years, where are we going? We've finished 03. You'll have seen on the plots there was an 04 and an 05 to come. There is again underway the work ongoing for a sort of medium scale upgrade of the advanced LIGO interferometers. Again, that's a joint US, UK, Australian sort of upgrade, again with support from and input from each nation. There's the sort of, again, the headline on the projected sensitivity improvements over at advanced LIGO, in terms of both range for binary neutron stars and for sort of canonical 30 solar mass and black hole binary inspirals. Those numbers, that 1.9 and 1.6, are of course they're the improvements in range, but then of course you have to turn that into events, and that makes an even bigger difference. So that should give us, again, greater event rate than advanced LIGO, and of course for individual events, and as we go into the future, there's another important point, that for individual events we have higher signal to noise ratio, and so we can just plain do a better job in extracting the physics from individual events. So there's a few, again, I won't go really into the technical details for this. There's a few different components to this upgrade. So there will be a staged implementation of those. Some aspects, in fact, we hope to have in place for 04 for the next run. Some of them will come after that, looking towards, again, a run in the future, about 1.5 to 2 years. The current runs have been about, the latest run I think was about a year, just a bit under. Again, with improved sensitivities again, and as I hope you're convinced from the previous plot, that is well worthwhile. And then LIGO India, again, when it comes online, will come online in this A+ configuration. It will come in not as straight advanced LIGO, but in the A+ configuration, so that it provides a comparable partnership with sensitivity in the network. And I should say a similar upgrade, again with similar targets, is planned again for advanced Virgo. So again, we have this matched set of instruments in the network in terms of capabilities. So that's the sort of medium term. In the longer term, there has been for some time, and there certainly is at the moment, quite a bit of work ongoing in terms of a future generation of observatories, what science they can do, what they should look like, where they should be, and so I'll give you a perspective on that. Because so far we've been talking about upgrading the instruments we have at the observatory sites that we have. But and it feels like this, well, it still feels to me at least like this field was born yesterday. 2015 was our first detection, so it seems like yesterday. But in fact, when you look back at the sort of construction timescale of these instruments, and the sort of commissioning and first runs were actually back to the early 2000s. We are now heading rapidly towards 2021. At some point, we will hit the limit of the current infrastructures, but again, we should also be mindful of the fact that actually the existing infrastructures have been there, parts of them for already 2 decades. So these infrastructures eventually will have a lifetime. We are not there yet. We're still well into exploiting what we have. But if we want to think about the 2030s, the 2040s and onwards, as you'll see that I'm going to talk about, again, and another important fact is keeping the capabilities that we have. Again, we can talk a little bit more about that. It makes sense for various reasons to think about new infrastructures. And again, as in many fields, this takes a long-term vision. what comes after the advanced instruments is not a new question, and it's one we've been working on since some time. Back again to the early 2000s, when there was a European support for a workshop in this area, followed on with a formal paper design study, with bring together a number of European countries to look at what the future capabilities might be. Again, this is a document, again, you may already be familiar with, that in 2011 published a design study for a larger detector, again 10 kilometers in Europe, and for a couple of different reasons, underground, and there are a couple of good scientific reasons for that, and also frankly in Europe finding a place to put such an instrument above ground would be non-trivial, but again there are also scientific reasons for putting it underground, and that's the Einstein telescope. There's been since the first detections, there's been considerable work and momentum behind updating that conceptual design. I've put up a link there, and if you go to that link, you will find a large amount of work that's been done by the consortium, again, of now many countries, many scientists, to bring that design report up to date and move it forward. Obviously, of course, the detection had significant, and the science capabilities then allowed us again to refresh the science case for third generation detectors, and much more broader work done also in terms of the thinking behind the infrastructures and the impact of such a future detector. And that is, again, has been a lot of work over the last couple of years on preparing the project to be submitted for the opening that there has just been in terms of an update to the S3 roadmap, again, that covers all scientific infrastructures in Europe. And so we've had a steering committee, a whole set of work in preparing the necessary submission for that, which has gone in. A list of some of that work there. Again, there's formal statements from a number of countries about their interest in supporting this. Again, it's part of the S3 process, as well as a large number of individual institutions who are, again, signed up to work on the project. Again, a busy slide, but to give you a feel for some of the scope of the activity that's ongoing, you'll see there's the S3 proposal submission, again, and there's a formal timeline to be worked through in terms of making a decision about what can enter the roadmap. But I wanted to just flag a couple of things in terms of the scale of the other work that's ongoing associated with this, in terms of pre-engineering studies, in terms of thinking about the sites and technology development. The field has done quite a lot of work on site assessment and site characterization. There are sort of two sites currently under significant study. One which is in a region of Europe which is sort of bordered by the Netherlands and Belgium and Germany. Again, so again, this is an underground instrument around the conjunction of those countries. So there's active work there. Supported by, again, as you can see, significant regional funds to support some of that work. Similarly, there's another site in Sardinia. Again, in each case, there's a sort of pathfinder facility associated with these to look at some of the necessary R&D. And again, significant regional and national funds going into helping with the assessment and characterization of those sites, and there'll be a process ongoing to be worked through to think about that, as well as a lot of background work supported in different ways for the underlying sort of R&D and engineering studies associated with the instrument. So that's the sort of European activity associated with third generation instruments. In the US, which has not had such a long history of thinking in detail about a third generation observatory, that also has ramped up in the past few years since the detection. And so there is now a NSF funded sort of conceptual design study for an instrument with the name Cosmic Explorer. Both of these instruments, I should say, have a target sensitivity that's about a factor of 10 improved in sort of sensitivity compared to the current advanced detectors. Cosmic Explorer has a slightly different vision for how to get to that sensitivity. This would not be underground. Proposal there is to put it above ground. It would not be triangular, it would be L-shaped. And again, there are pros and cons to each of these designs. They end up with slightly different sensitivities, as we'll see in a bit. But that's, again, a conceptual design study underway. I've put in the link there, again, and so you can happily click on that and find out more about that instrument. In terms of timeline, clearly it's further behind. It's at the conceptual design stage, but of course benefits from all the thinking that's gone into third generation observatories more broadly. This, you'll see, I'm sure there's a caveat somewhere that says very funding dependent. Again, it's only at the conceptual design stage, but in the US there is a quite formal and well understood process to work through, again, in getting from conceptual design potentially to an instrument, and so that's relatively well understood in terms of the potential process. And there's again a lot of documentation already you can find about the Cosmic Explorer instrument. To give you a feel for what these would mean in terms of transient capability, this plot it's got redshift up the left-hand side and total source mass frame along the bottom. And it compares the capability of advanced LIGO with what either ET or Cosmic Explorer would be able to do. And you can see, you know, we are for various potential masses heading right back again to the early universe. The slightly different designs of the instruments again optimize them for slightly different science, and I'll talk a little bit more about that. There's been a lot of talk about, again, some of the science you can do with binary neutron star, and particularly in particular binary neutron star, but also binary black hole sources. But I wanted to just give a feel for what the scale of the difference is in terms of what these instruments will be capable of. I actually picked a different example, which is actually in tests of GR. So this is a slide from Sathya Prakash and one of my colleagues, who, you know, as an illustration shows what the equivalent signal to noise ratio would have been for the first detection, so GW150914. In 01, when it was detected, it had a signal to noise ratio of about 25. With the detector network in the late 20s, that would translate to a signal to noise ratio of 250. With ET and Cosmic Explorer, it's a signal to noise ratio of Cosmic Explorer over 2000. And that is a very different kind of science that you can probe once you have that kind of precision in terms of the signals that you're able to detect. And I think certainly Sathya has been keen to impress upon people that requires a different way of thinking from theoretical colleagues about the capability that these instruments will have. So this is quite you know, a significant advance in terms of thinking about the sorts of science that can be done. Another way to envisage this is, this is a slide from Evan Hall at MIT, that again, you'll see redshift as we move out from the center of the plot. The colored lines, again, those circles are the sort of capabilities or ranges of the different instruments we've talked about. So you'll see again a sort of pink line that says 03 there. So that's the sensitivity of the third observing run. In light blue, what advanced, apologies to the colorblind, in light blue, what advanced LIGO Plus would look like, and then what things would look like again, say for ET in green. And those little white dots are binary black hole coalescences. The yellow dots are binary neutron star coalescences. So basically, in some mass ranges, the third generation instruments would essentially detect every binary black hole coalescence. There has been no black hole left behind. So it's a very different capability than we have at the moment. I've talked again about CBCs. I won't go into detail on this slide because I think people again have already talked about the different sorts of science that can be done. Precision cosmology, again, once we have this vast number of sources, the sort of probes of neutron star equation of state. I mentioned the capabilities in probing tests of GR, a whole set of exciting science targets. And I mentioned also that dependent on the exact design of the instrument, whether it has better low frequency sensitivity or high frequency sensitivity, or how many detectors you have in a network, you're probing different potential parts of science capability. And so when we think about the future and what the future might look like, that's an important thing to bear in mind. And again, in addition to the two instruments that I talked about, again, where we're looking at timescales that are out in the 2030s, late 2030s, there again have been some discussions about, of course, those are two. Currently, we were looking at a 5-6 detector network. For the third generation, there are those two, and there have been thoughts around what capabilities might complement those, for instance, at the high frequency range. Again, if we look at the previous slide, you can see the neutron star sort of post-merger phase, neutron star equation of state. Those are higher frequency signals. Again, what a dedicated capability might look like, and so you'll see down in Australia there sort of light green a potential concept that could add additional capability to a future network. So just to finish, our current detectors have delivered amazing science in the few years that they have been operational, but they only access a small fraction of what's out there. We haven't talked about the technical details. There's, of course, a whole bunch of technical challenges that need tackled to make these a reality. But we think we can see a way forward to having a third generation that would be, a huge step forward from where we are at the moment, and planning is already underway. And I will stop there.
Thank you very much, Sheila. The future is obviously very bright for gravitational wave research. Neil, do you have some questions?
Yeah, well, there's one here, and I've got one of my own as well. I'll squeeze mine in quickly first, which is, one hears, as somewhat of an outsider in the field. Every now and again, you see a paper saying, oh, well, one could make a gravitational wave detector using some weird quantum effect or another, atom interferometry or something of this sort. But these don't seem to feature, as far as I can tell, in actual planning for real hardware. Is there a good reason for that?
So a couple of things on that front. Yes, so there has been for some time, our colleagues in the atom interferometry field have been working on prototype systems. They've been thinking, so there's I should say, you're right, there's atom interferometry, but there's a whole bunch of other sort of, more exotic quantum-based proposals for things. I would say atom interferometry, I think, is very interesting. As a field, we have quite often talked to our atom interferometry colleagues. They are still in the demonstration phase of what the capabilities are of those instruments. And I think it's very interesting technology. I think developing prototypes is the right thing to do. And it's the same thing there, frankly, to some extent, as it is for those quantum proposals, which is people spend a lot of time looking at the capability of how something might detect a signal and not really thinking about what the noise in the system is. And it's always the noise that's the issue. So, and the capability to, the in principle, could you detect a signal is one thing, but sadly, and certainly in the gravitational wave field, we spent a lot more time, but many more years of our lives still thinking about the noise than we have about the signal. And so it's not that some of these aren't interesting ideas, but for many of them, it's that thorough noise analysis in terms of practical implementation that still it requires a fair old bit of work, but they are interesting. And so again, the other thing I would say in our field is we are highly adaptable to new technology. Sort of, we are absolutely open to things that come along, and so we do regularly chat to these folks. But that's usually, it's always the noise. What's the noise in a noise analysis?
Okay, thanks for that. I better press quickly on because we've got some more questions coming in. So one from Paul O'Brien. Is there more science overlap between LISA and the next generation of GW detectors? I guess he means third generation 3G compared to LISA and I suppose 2G current detector.
So I think people have been thinking more about that, yes. And I think actually we're starting to come, I mean, you really want both, and you want them operating on a time scale, because what I talked about, all those black hole binaries that are going to coalesce in the ground-based band, but earlier in life, they are going to have been rotating in the LISA band. And so when depending on the mass of the binary, LISA will see some of these in the in-spiral phase, and won't see them coalesce, but they'll go through the LISA band. They'll spend quite some time there. And LISA actually will be able to provide information that will tell when these systems are going to coalesce in the ground-based band. And so it's a point ahead capability in some ways of this. And I think that's just one example. It's also in terms of the complementary mass ranges and the additional information that we're going to get from that. LISA's also looking at a very different mass range in terms of black hole binaries, and you're going to want to put all of that together to get the full story of the astrophysics out.
Okay, so one from Phil Evans.
Sorry, Neil, we're running rather late.
Okay.
We kind of need to move on, I'm afraid. So these last two questions have come in they're just going to take too much time. So I encourage people to mail Sheila if they have further questions. We ought to move on now to Joe Lyman, who is a future leader fellowship holder at the University of Warwick. He's going to tell us about a relatively new facility called GoTo.
Thanks, Julian. Hopefully you can see my slides and hear me okay.
Yep.
The organisers for the opportunity to talk to you, as Julian mentioned, about the Gravitational Wave Optical Transient Observer Project, or GoTo. And obviously as part of this meeting, I'll be specifically looking at the multi-messenger astronomy that GoTo enables. Now, to this audience, I don't think I need to do too much of the science motivation, but I just do want to raise sort of, if I can get it to move to the slide, just raise the issue that we now know of a few different messengers from the universe, from a handful of different sources. There's a non-exhaustive list shown here. But for the purposes of this talk and what I'll be discussing as part of the GoTo project, as you might guess from the name of the project, I'll be particularly concentrating on gravitational waves. And in particular, as we're an electromagnetic follow-up facility, we're interested in those that give rise to some appreciable electromagnetic signal. So we're looking at those sources that have at least one neutron star as a component. But that's not to say that we're not interested in the top half of this slide. Of course, we are interested in following up essentially any sort of multi-messenger signal, but that's not what I'll be concentrating on here. And of course, when you're talking about gravitational waves and multi-messenger, you have to sort of name drop 170817. Don't want to talk about this event at all, apart from to point out there's a very nicely timed archive review article on this, which I believe came out yesterday, coincidentally co-written by our next speaker. So I would suggest you to read that for more information on this object. But I was just really raising the object sort of to give some perspective that it's been more than 3 years now since we've detected this object. And as we heard from Sheila, we've got now large catalogues of gravitational wave transients, but really this is the only multi-messenger example we have, the only credible electromagnetic source associated with them. And so on the right-hand side here, you have a whole bunch of parameters from a bunch of gravitational wave detections from this most recent observing run, the first half at least. And I've just highlighted on the right-hand side with an asterisk those where there's at least one neutron star system. And so, as I mentioned, this is where we expect potentially some electromagnetic signal. Now, unfortunately, we're down to only a handful from the entire gravitational wave transient catalog. And of those, a lot, they were either much too distant or much too poorly localized to really put good constraints or have good chances of detecting the associated kilonova and electromagnetic signal. I believe the very first talk this morning, Udi was mentioning that 170817 is not going to be the typical case. This is very much a sort of a once in a many years event, and this is more like what we should be expecting to have to follow up as part of these follow-up campaigns. And so I've unfortunately not updated this for the new COVID delay, but you saw the example that Sheila gave in the previous talk. So maybe shift 04 by, what is it, best part of a year or so to the right-hand side. We're expecting 04 actually to start somewhere around the mid 2022. And so the fact that we only have GW 170817 is as a gravitational wave multi-messenger event, is probably going to be the case, at least for the next year or two, as these detectors are down for various upgrades. But I would say, as a sort of an electromagnetic community, we've heard a lot about high energy electromagnetic missions earlier on in the day. We're really sort of targeting 04, and 04 is the time when we want, as a community, to have all the resources and tools available to us to really pounce on any potential trigger coming out of LIGO, Virgo, and the other detectors that could potentially harbour a sort of a kilonova or an afterglow-like signature, because we know about the scientific yield that these sorts of objects can provide us with. And so that's really all the motivation I want to give for the GoTo project. So the GoTo project is a project being led out of Warwick in partnership with Monash University in Australia. There's a host of other collaboration members from the UK primarily. We also have interest from Finland, Thailand, and the Canary Islands. And so it's a growing collaboration now building this electromagnetic follow-up facility. So just to sort of look at the design and the philosophy behind GoTo, as is probably obvious from the project name, is really a dedicated wide field optical survey. And the primary science, the primary driver for the entire project is to detect the electromagnetic counterparts of these gravitational wave sources. And the design itself really builds on a heritage that Warwick has for creating large arrays of small telescopes in order to build, firstly, cost-effective, but also scalable and very adaptable wide field surveys, rather than just one monolithic telescope. You're talking about lots of small telescopes on a small number of individual mounts. And that inherently gives you this scalability and adaptability. And so when you're designing a sort of wide field survey, particularly one to be following up gravitational wave events where we know that the localization uncertainties are significant, then there's sort of three axes for your survey that you want to maximize. First of all, you want to be able to cover a large area. Of course, we know that these are tens of square degrees at a minimum currently, talking up to hundreds or maybe thousands of square degrees on the sky for these localizations. But you not only want to cover that area quickly, you need to cover it to a significant flux depth. The expected electromagnetic signal from kilonova is much more intrinsically fainter than supernovae, for example. So we need to cover a large area to a decent flux depth. And of course, these two together combine to into a single axis that you can think of as like the volume that you're probing where your potential counterparts could lay. And the third axis is, of course, cadence. So these objects on the sky are not alone. The night sky is changing, ever changing, particularly in the optical. We're fighting against all sort of interloping supernovae, variable stars, galactic outbursts. So when you acquire a trigger externally and you follow that up in the optical, there's a whole bunch of other sources that are changing in the night sky within that volume, and you need to really reliably hone down into the single objects that you care about as the counterpart to your trigger. And so by having a very high cadence sky survey as part of your project, you build up a very good picture of what's going on in the local universe. You know what things are changing. You know when a supernova is exploded, and such that if it exploded before a gravitational wave trigger comes in, for example, then you can immediately rule that object on sky out of your consideration. And so that's the sort of very much the design philosophy of GoTo. And so what does that look like in reality? And so I'll spend a few slides talking about the GoTo prototype system, which is just coming sort of to the end of life now. We're very much in a transition period to new hardware and major upgrades. But this was running for a couple of years, give or take. And so I'll just spend a few slides talking about some of the details of that system and the results from it. So the first system was 4 of these unit telescopes I mentioned in this array configuration. You can see in the bottom left. These are 40 centimeter telescopes located on La Palma. And La Palma is an excellent observatory. It means that we're right next door to some excellent facilities, in particular good robotic spectroscopic follow-up facilities, which means that when we detect something of interest, we only have to go next door in order to trigger detailed follow-up. I will just highlight also CTA, of course, another big project where the majority of which will be on La Palma, and that's under construction now. And that really opens up some new windows in the sort of medium term for GO2 in terms of multi-messenger astronomy. A little bit more detail on the actual hardware of the system itself. So I mentioned the 40cm telescopes. We've got 1.25 arcsecond pixels. That's plenty enough resolution for what we require for this science. Each of the telescopes does have a filter wheel, so we can get color information for anything we detect. In reality, during the prototype stage, we really concentrated on the L band, which is essentially this orange wide field filter you can see in the top right. And that's just it, really, because we want to get the most throughput. You want to go as deep as possible. You're not particularly interested about color information just yet. Each of the unit telescopes had about 5 square degree field of view. So this is Andromeda in the bottom left. That's a field of view of one telescope. So in the prototype stage, we were talking about 20 square degrees or so in terms of the total footprint for the system. And where we get into in terms of depth on the sky is where we want it to be. We want to be able to get to about 20th, pushing even beyond 20th within a few minutes of observations in order to detect kilonovae at typical gravitational wave horizons. And we're able to get beyond 20th in just a few minutes of observations. So that's great. So how the hardware itself actually talks to each other, and it relates to the environment that it's in, and also links to external streams of alerts coming from, whether they're coming from GCNs via gravitational wave triggers or GRBs. This is all contained in the GTEx software, which was written by Martin Dyer, and I would direct you to his 2 papers there for more information on this side of the telescope control system. But rather now I'll sort of look at the results. So this obviously populates an observation schedule and tells the GO2 system what it needs to do. And so now I'll sort of switch tack and look at actually what we did during this prototype stage. So you can see here a sky coverage map of GO2, and you can see that we've covered the entire northern hemisphere down to about -30 declination multiple times now. So this is covering a period from March last year until just a few months ago in August. So a typical number of times we observed a patch of sky in this time frame was about 20 or so. There's a few notable outliers. So a couple of the internal tile numbers, which are labeled, I believe, are related to M31. I think one of them is, which we hit every night when it's visible, for example. But the vast majority are sort of, 20, give or minus a few on the sky. And if you factor in some major shutdowns, primarily due to COVID, there was a several month shutdown on the island because of the outbreak. But we also had several hardware downtime, technical upgrades and things like that. If you fold all that together, this number of times a tile was observed translates to a mean revisit time of somewhere around 12 days or so, which is not great for finding serendipitously interesting transients in your data, but of course we're still just working in this 4-unit telescope prototype stage. But if we look more generally at the sky map itself, you'll notice it's not homogeneous coverage of the night sky, and the sort of eagle-eyed amongst you will actually be able to pick out probably some of the gravitational wave localization maps within this sky coverage, and that's because GO2 played a major role in the follow-up of gravitational wave triggers during observing run 03A. The full details of this are given in Ben Gompert's 2020 paper, but a few headline numbers. We did trigger on 32 gravitational wave events in this first half of this observing run. As I showed earlier, this full gravitational wave transient catalogue, the vast majority of these are binary black hole systems. Now, from an electromagnetic stance, there are models that maybe predict very weak or very peculiar electromagnetic signals, but for the most part, we're not really expecting anything out of these. But nevertheless, they're excellent testbeds for neutron star systems. And because this is entirely what GO2 is designed for, why not? This is excellent stress tests for the system, and it performed very well. So we had many hundreds of square degrees coverage on the night sky of the sky maps, even with this 4-unit telescope prototype system. And importantly, we were getting down to the depths we wanted to over these sky maps. We were reaching sort of depths where if there had been a kilonova in the map, we were able to reach those depths over those sky maps. And happily enough, when the system was observing and the weather allowed and various things like this, and a trigger was issued by LIGO, we were onto the sky map in seconds and typically within a few minutes of that trigger being issued. And so it's really important for getting these very early detections and sort of notifying the community. So that was really nice to see. So that's the prototype system. I mentioned that now we're really going into a stage of major hardware upgrades, getting prepared essentially for 04. 04 is our ultimate deadline. Go-to at full design will be ready for 04 once the next upgrades are complete from the gravitational wave side of things. So I'll spend a couple of slides now just looking at what Go-to at full design looks like then. So in prototype, just to re-emphasize, we were talking about 4 unit telescopes on La Palma. But Go-to at full design is 2 sites now. So we have La Palma and sort of almost antipodal, we have Siding Springs in Australia. And rather than just 4 unit telescopes at each of these sites, we have 16. And so we have 32 telescopes in total, each with a field of view of about 5 square degrees. And what we really see is that Go-to can hopefully play a key role in sort of this concerted global electromagnetic follow-up effort, particularly from ground-based wide field surveys. Some of the other major players in the game you can see are highlighted here. In Palomar, you've got the ZTF, for example. At Hawaii, there's Atlas, Lucia to represent the various surveys ongoing there, and Chile in general, where there's a whole host of telescopes. But you see that Go-to actually fills in some quite nice longitudinal gaps we have in our instantaneous coverage. And so the hope is that regardless of where one of these triggers is localized to, we're able to get onto it as a global community almost instantaneously, unless of course it's behind the sun, which will no doubt happen. In terms of the evolution of the project itself, I mentioned that it's this scalable approach using this array-based telescope. So it's not just one monolithic telescope where the project is all or nothing. We'll be able to scale up the survey from the left-hand side, as I mentioned, about a sort of mean cadence of about 12 days on sky for the Go-to 4 performance, all the way up to Go-to 32, which is at full design, where we'll have full sky coverage, mean cadence of about 2 days. And that's when things start getting interesting for finding serendipitous transients. You'll be finding young objects in your sky survey just from the very fact that you're observing with such high regularity. But also it means that we know what's going on in the local universe to a high degree of certainty, such that when a new trigger comes in, we can be confident to immediately rule out the vast majority of changing objects that could potentially be the counterpart and really help sort of weed down to that single counterpart that we're looking for in each sky map. In terms of on sky, each Go-to site, so the Go-to 16 shown here, you can, for example, take that to be La Palma. We'll have an 80 square degree footprint on sky, so that would obviously be doubled. There'll be the same footprint for the Australia node. And so going back to these axes, as I was mentioning, with Go-to, we're really pushing down the area and cadence axes. So ZTF perhaps gets slightly deeper than Go-to, but Go-to makes up for that because we can cover the entire sky. We've got a northern and southern node, and we've got a significantly larger area at each of those nodes themselves. So that's what Go-to at full design looks like. I'll just spend a little bit of time looking at some of the recent changes that are ongoing with Go-to and sort of look at a current status of the project now. So the major change has been a new choice of unit telescope. So the prototype unit telescope had a few issues. Very recently, we've put on a new set of hardware, which is this new telescope tube you can see in the top right. And basically, we've already established that the performance is significantly better than the prototype system, and so this is the design choice that we're going for now, and we'll have 32 of these telescopes. And because we've got a performance boost from these ones, we're expecting that actually our projections for the survey in terms of cadence and depth and things like that will actually only improve with this new hardware, which is great. The second dome, which is in the top right of the La Palma picture there, you can see there's a second dome being closed. So that is due to host the second mount for La Palma and 8 of these new unit telescopes. That's due to be delivered in the next few months there. So at that point, we'll have significant capability on La Palma with GoTo. And again, just sort of stressing this array-based approach, it means that the project is not finished, but still La Palma it will be a significant transient machine. For GoTo will be a significant transient discovery machine. Now, during 2021, we're not expecting, of course, any gravitational wave triggers, as we were hearing that they're down for various upgrades. But of course, there's plenty of things we can follow up with this significant amount of hardware from La Palma. There's short gamma ray bursts. Of course, we know that those now are produced by neutron star mergers. Just because you don't detect the gravitational waves doesn't mean you're not expecting kilonova signatures in the afterglow, for example. We've seen a huge increase in the number of neutrino alerts being put out recently. So these are, of course, other viable multi-messenger alerts to trigger on. And as part of the collaboration, there's also plans to perform sort of sub-sky surveys where we would target particular patches of the sky for very high cadence extragalactic transient searches, as well as performing galactic science, so essentially just staring at the galactic plane for many hours and looking for sources that vary on timescales of minutes and hours. If we switch and look at the southern node, so look at the Silent Springs, Australia, construction has started there, and I believe the first dome is en route as we speak. So that's been delivered now to Silent Springs, and it's really the development of that site will take over once La Palma is completed, essentially. So switching now from hardware into software and look at some of the things we've been doing with GoTo on the software side of things. So firstly, GoTo data has been used as a sort of test bed, as a surrogate for the Rubin data to throw it through the LSST software stack. So there's a couple of papers by James and Lydia that were doing this, so essentially throwing GoTo data through the LSST software stack, and that's developed a sort of feedback cycle with the LSST software developers, and has actually led to GoTo contributions to LSST software repos. In terms of our in-house pipeline, so that has been rebuilt from the ground up, primarily driven by the new choice of hardware, but also the prototype pipeline had a significant number of shortcomings and inherently was difficult to scale. Whereas now we're going from 4-unit telescopes processing up to 32. We need an inherently scalable solution, and so that's been in development now. As part of this, there's a web-based Marshall system, which is just a web page user interface, essentially allows human collaboration members to directly access new sources that GoTo is discovering in pseudo real time. And this Marshall system will pull in external catalogs, external contextual information about the discovery and about the detection to allow humans to make an informed decision on whether it's an astrophysically interesting object, for example. And we have now in the capability that once a human, for example, thinks an object is of interest, we can really take advantage of the fact that GoTo is sat next to some really world-class follow-up facilities. And just with the click of the button in this interface, we can trigger, for example, the Liverpool telescope shown here. We can get a nice low-resolution optical spectrum of that new source in order to classify it. And so it's really sort of capturing the idea that GoTo is sat amongst this set of world-class facilities. And so the last piece of software I just want to talk about is how we actually get to this point here in the GoTo Marshall of sifting through huge amounts of data to get to the very small amount of astrophysically interesting data from a transient point of view. So from a point of view that I want to find something new that's only just happened. And so that requires a model that is able to sift through huge amounts of data, and essentially you have to apply appeal to machine learning techniques. And so this is a piece of work that's just been submitted by and led by Tom Killistein, a PhD student here at Warwick. And so what he's developed is a Bayesian convolutional neural network model, which works directly on the pixel data of the GoTo survey, but this is applicable to any sort of wide field survey, we believe. And there's a few novel features about this model which are really cool, but I don't have time to talk about those. There's one that I want to highlight is the idea that we've made this model into a transient optimized source recovery model. And that is that we're optimizing for the kind of objects we want to find. We want to find kilonovae and AGN and TDEs, for example. And so this is all completely automated, the whole system, which is great. And the transient optimized side of things, you can see the effect of this in the bottom right sort of box here. So in each of the panels, the green bar chart is when we include the transient optimization, and the dashed line is when we don't include transient optimization. And so the y-axis is the recovery rate of known spectroscopically confirmed transients. And so the higher is better. Ideally, you would be around 1, but that's very difficult. And you can see if you take the top panel that across the entire magnitude range, once we get to the sort of noise limit of the go-to images on the right-hand side here, obviously things fall off. But essentially flat across the entire discovery range, we obtain a notable increase in our recovery rate, which is really, really great. So we're recovering more transients than we would naively do without this optimization. And a really cool result, I think, is that if we compare this now instead of brightness to host galaxy offset, we get significant improvements in the centers of galaxies. And so things like AGN TDEs, which we expect can produce multi-messenger signals, we want to be able to recover these robustly in our data. And so the inclusion of this model really is helping us to do that. And really the whole reason why we're going through this spending so much time and effort building these really state-of-the-art models is we want to minimize the time between discovery and characterization. We heard earlier on this morning, there's a whole host of science you can do by really collapsing that timescale and going from a transient exploding to actually taking detailed follow-up observations of it. And so that's why we're already thinking the next generations of this model, which if you take the sort of typical follow-up timescales for when a transient occurs on the left-hand side to actually scheduling detailed follow-up on the right-hand side, we want to scrub out the sort of need for a human in the middle. You can feed a model all the information a human has. It can pull in contextual information. It has access to the pixel data to look at the significance of the detection, the confidence of the detection. You can teach it about what is an interesting object for your particular trigger. And so we really want to kill this time where humans, maybe get down to minutes if you have someone set up during the night and doing this in real time, but the model doesn't sleep. So that can make this decision in seconds, and it can trigger robotically at other telescopes in minutes. And so that's really, really sort of like the end game for where we see these types of software developments with GoTo and for other surveys. And so I just want to make look at one final point before I throw up my summary slide, and that's to look at GoTo in the evolving face of gravitational wave follow-up. So we heard a lot in the previous talk by Sheila, the general trend of gravitational wave detections. We're moving to better localizations and larger distances. So you can see, particularly in the top right panel, the effect of going from 03 to 04, the sort of the median, just the general trend of the localization uncertainty is shrinking, although some large diversity does remain. But GoTo in its array-based approach can evolve to meet a lot of these needs. Once we get to the point where we realize, okay, our on-sky area is overkill, for example, we can then start co-pointing our unit telescopes to provide more depth over a smaller field of view, or perhaps provide simultaneous color information if it's found that that's a sort of key discriminator for finding these counterparts. And because we've got multiple sites and multiple mounts, we can employ multiple search strategies in tandem for any given object in order to maximize our recovery chances. And I just want to finish on one final point, that GoTo really is dedicated to this counterpart follow-up science, this gravitational wave electromagnetic science. We're not piggybacking on another survey which has other science or funding commitments. We can spend as much of this time, much of GoTo's time as we want doing this science. And so we can chase up in the top right here, where you have very poorly localized events. These will probably be ignored perhaps by other surveys as the rate of detections goes up. But this is exactly where GoTo can sort of fill in that niche and really start getting the statistics on the recovery of these sorts of events, primarily just because we're not tied to any other sort of commitments. And so with that, I'll leave up my summary slide, and rather than repeat myself, I'll just finish there and say thank you for listening.
Thank you very much, Joe. Neil, do we have questions?
Yes, certainly we do. First one from David Buckley. Nice talk. How do the GoTo capabilities compare to Black Gem or other follow-up networks in terms of survey speed for GW counterpart searches? Yeah, so taking Black Gem specifically, they're going, if you can sort of recall back to this 3-axis I was talking about, they're really going down the sort of the flux limit to some sort of a little bit of area. Maybe I can go easiest if I go back to the footprint. So we're talking here, you've got Black Gem on the left.
So for each individual telescope, they have about a 2.7 square degree field of view. Of course, GO2, we're very much going down the area. So for the poorly localized events, GO2, is probably going to win out. The difference is that Black Gem can go significantly deeper. Their telescopes themselves are larger, and they're putting a lot of effort and a lot of money into really developing the optics and the sensor systems for these. So they can go significantly deeper than us. So it really comes down to, we're expecting a huge diversity in the gravitational localizations. Maybe when it's really well localized on a scale of square degrees, then Black Gem will be easily able to cover the sky localization. But if there's 100 square degrees or 200 square degrees or even more to survey, then Black Gem really can only pick and choose its locations. It's only really going to be able to look at the very highest probability regions. It's going to have a difficult time really getting across huge swathes of the night sky.
Okay, question from John Morell. There are claims in the literature, paraphrasing slightly, of stars disappearing in external galaxies where they've presumably collapsed to a black hole, but without a supernova. Do you have the capabilities to look for those in your current search engine?
Yeah, so sort of fundamentally, the issue is very similar. It's that you're looking for something that's changed on the night sky. Now, we've obviously, up to this point, we've really focused on anything that's new on the night sky. So we're looking for something where there wasn't something in our previous image, and then there's something new. But the problem is just invertible. I mean, at some level, you could just flip the pixel values if you really want to, and it's exactly the same problem. So this is certainly something we're thinking about, particularly for very nearby galaxies. We're getting down to depths where we would see disappearing stars. And so, yeah, this is definitely something we're thinking about, particularly as part of this pipeline rewrite I was mentioning.
Okay, and last one, it seems, from Andy B. Have any simulations been performed to estimate the effect of Starlink on GO2's science capabilities? This is the satellites, I guess.
Yeah, no, so I don't have anything sort of quantitative. I know that it's very particular times of the evening, particularly around twilight, there can be some disruption. It does cause a headache for us. I don't think it's at the level where some people were fearful that it would be. I mean, it maybe affects a couple of % of your pixels. I mean, please don't quote me on this. This is what I'm sort of remembering from hearsay. It's of order, a few % of your pixels are affected around a specific time of the night. So we're not talking about sort of huge whitewashes across our field of view or anything like that. But it is, of course, a headache from a data processing point of view, because you need to reliably find those streaks and do some appropriate masking to know that it's not of astrophysical interest.
Okay, thank you.
Okay, I think we ought to move on. So thank you very much, Joe. Next up, we have Raffaella Margutti, who's an associate professor at Northwestern University in Evanston near Chicago, who's going to tell us about time domain astrophysics with LSST.
Thank you, Julian. I hope you can see my slides.
Yep.
Awesome. It was a true delight to wake up this morning, early in the morning, and with all these talks about the future, and also hearing some familiar voices from the Swift family, where my scientific adventures started from. So thank you so much for having me. So yeah, so today I'm gonna try to give you a tour about what's going on in LSST, and specifically here I'm wearing 2 hats. So I'm here as part of the executive board of directors of the LSST Corporation, but also as member of the Transient and Variable Star Collaboration. And specifically, I'm leading the gravitational wave multi-wavelength characterization within the TVS. So first of all, here is a picture that was shared by Zelko a couple of days ago at the first science collaboration meeting of LSST, so it's December 9. The message that he wanted to convey is that, yeah, LSST is becoming real and more real with time, and the dome is there, so we should get excited about it. So I will start with a little bit of a tour into the LSST ecosystem, which might be a little bit different from the surveys we have been hearing about so far. So, and I'll start with the link, the LSST, what I call the LSST lingo. So first of all, there are different pieces of LSST. And of course, there is the Rubin project. So the people in charge of building the telescope and making it perform. There is the LSST Corporation that has the role to provide financial support. I'm part of the LSST Corporation, and I would say is a very good time for your institution to think about joining the LSSTC, as there will be and there are funding opportunities. So if you're thinking about getting more involved with the LSST science, so you're thinking about finding funding for a postdoc, LSST Corporation can actually help you out if your institution joins the corporation. I'm going to provide links so that you will have all the material to find out more. Then there is the SAC, the Science Advisory Committee, that is composed by individuals of the order of 10. You can see the composition online. And this is the organism inside the ecosystem that is in charge to give the project science advice. Then there is the SCOC, the Survey Cadence Optimization Committee, which is a more recent one that has people that have been nominated by the SAC. And the goal of this SCOC is to actually come up with the plan for the initial plan for the 10 years of LSST. And finally, inside the ecosystem, there are the scientific collaboration, the science collaborations. There are many of them, and I'm part of the Transient Variable Star, which I think is probably the collaboration that is the most relevant to the people on this call. If you want to join, there are all the information online, and please do. So the timeline, where are we right now? This is the original official timeline from the LSST, from the Rubin project website. I heard from Zelko a couple of days ago that, not surprisingly, there will be delays for COVID. How much that will be, I do not know if there is a formal word about it. It's probably of the order of months. That's what I've heard. So when you look at this timeline, think about that there might be some months of delay. So what are the main modes of operation that have been discussed for LSST, and what are those that are not here yet and that we are trying to actually push to have? So this is one quick slide to bring everybody up to speed. So first of all, most of the time of LSST is going to be spent in this wide, fast, deep survey in these 6 filters, U, G, R, I, Z, Y. And what is up for discussion right now is what is going to be the footprint of this survey, what is going to be the sequence of filters that we will get. The remaining part of the time is will be allocated to other time domain experiments or experiments of other sorts. And there are already 4 deep drilling fields that have been selected and that I put right there in that table. A deep drilling field, you can think about that very conveniently as one single pointing. Those are regions of the sky that will be covered 5 times more often than the rest of the sky of the wide, fast, deep survey. I hear that I heard at the workshop a couple of days ago that a 5th deep drilling field informally has been probably selected to be the Euclid one, but I don't think there is any formal word out of it, and there might be more than 5. Then what is has been discussed is also the possibility to have rolling cadence. What that means is that instead of having a homogeneous coverage of the sky at any single time of the survey of WFD, the thinking that is very much in our minds of people that care about time domain is to reallocate fields in a way that so that we would have at least some portions of the sky that will be covered more often. The reason why that is a need for us is going to be clear in the next couple of slides. There have been also discussion for mini surveys, and the convenient thing to think about mini survey is like a deep drilling field that extends for more than 1 pointing. That's how I think about it. And then I would like to emphasize there is one thing that is not appearing on this slide, which is target of opportunities. So right now there is no formal word that there will be really happening. I think that is absolutely likely that will happen, but as you can see that they're not yet here. So let me give you a flavor of what the WFD would do here. I'm using a baseline cadence that is no longer the most recent one, but the basic concept is the same. So the one concept that I want to bring, that I would like everybody to bring home, is that when we think about LSST, very often I hear, yeah, LSST is gonna cover each patch of the sky every 3 days, which is absolutely true if you mean in any filter, but not in a single filter. And if we do the same experiment in the same filter, the delta T in between two visits, and here I picked the R band, you can see that's much longer, it's 15 days. And for anybody that does is interested in fast transients or kilonovae, it's absolutely not what you want. Just to visualize what that means, here I've been very unfair, and I selected type 1a supernova a little bit far away, but forget about the flux, so the error bars, they will shrink. But what you can see is that the number of times we would get on target on a random type 1a is actually not that much. Our light curve would not be well sampled in the wide deep fast. And if we go into the deep drilling fields, yes, things get way better. So we have 5 times of the order of 5 times more observations of the same field. So absolutely better. We pay a price because the drilling fields are 4 or 5 fields, field of view of LSST. So this problem is not new. I'm sure I'm saying something that is absolutely obvious to many of you. And that's why back in 2018, in fall 2018, when there was the call for white papers for cadence, effectively cadence white paper, the community answered very, very vocally, the time domain community answered very vocally, saying, hey, the WFD is not what we want, is not what would maximize our science. Very differently from Go-To, LSST has to make everybody happy, or has somebody put it as to try to minimize the unhappiness of all the scientific areas. So time domain is not the only player. Nevertheless, we made the point. I would like to emphasize here for people on this call that 2 days ago, there has been issued a new call for what are referred to as cadence notes. It's just like another white paper. And the deadline is March 15 of next year. And so what is going on right now is that the project took the suggestions that we put in our white papers in 2018. The SAC deliberated on which proposals to try to implement on the simulations of LSST. The project ran those simulations, and they are now evaluating what is the best cadence in a quantitative way, trying to take into consideration all the scientific areas where LSST wants to perform. So we still have the way I look at this cadence notes call is like one of the last chances to voice our disagreement if that is there. Here I put a little extract from the call, and if you Google online LSST cadence notes solicitation, you will see you will get to this page. All right. So now I'll switch a little bit gears and try to go more on the side of the science that we want to do with LSST, which at the end is what motivates us to try to change the cadence or implement new observing capabilities on LSST. And here is how I think about this discovery phase space is luminosity versus time, and there are some time scales that are of relevance. And we have been extremely good so far in sampling timescales that are the order of a few weeks, typical luminosity of a supernova. All that area, gray area, has been sampled. I don't think that should be our focus. what LSST, and we have thousands of events there, what LSST can do really exceptionally well without any change in the current cadence is providing us with a view of pre-supernova outbursts. So this is a place where LSST, well, the time scales are long, and what we really like is the depth that LSST gives us, and this, at the end, this 10 years view of what those stars were doing just before exploding. The other place where LSST will perform without any change of strategy is just giving us for free a lot of very late time light curves of the nearby events just because of the depth. The two places that for me represent two places of discovery are fast transients, and the very fast transients, and the counterparts of gravitational waves. And those two are in red because right now, LSST with the current design of the strategy is not going to perform particularly well. However, I do believe that those are absolutely interesting areas. And of course, there is this third axis that is absolutely important, which is how rare these transients are. So LSST, in principle, I would say potentially provides the volume. So if we want to go and try find something rare, well, LSST potentially is the instrument to use. But there is an however that will become clear in the next slides. So another way I think about LSST is that fundamentally we have two ways to make progress in science in time domain. And the first way is to collect a lot of events. So very large sample studies where we give up on the dream of having spectra of our transients, and we do a statistically based classification based just on light curves only. The second way is the one that I find more appealing for me, for the way for my specific interest, is to try to go and find the rarest events that are there, but we still don't know that they are there. And to do that, we need something that identifies these very rare events in the flood of things that are absolutely uninteresting. We will have to rely, as Joe was alluding to, on artificial intelligence at the end. So anomaly detection for me is going to be one of the pieces where we should invest a lot of time in the next few years. So the key problem is that what we want is to find something interesting and to find it promptly. So we want to solve this problem of going from data to discovery. And this is where brokers come into play. This is where the artificial intelligence comes into play, try to match all the information known of the transient with current catalogs. The efforts that we have right now in the literature are divided up in two categories. There are light curve classifiers, where the exercise is conceptually very simple. We try to infer what a transient will do based on minimal information. And there are many flavors of those in the that you will find out there. One of my favorite is rapid. So the goal is to get on target early, which is the difficult thing. Infer the properties of something at very early times based on almost no information. The other piece of information that is there and that I particularly like is to use a context. So use contextual information, and that's something I very much like that also Joe alluded to with GoTo. They're doing that as well. So this is an effort that I started here at Northwestern, where we are querying all the catalogs, existing catalogs, and trying to reconstruct the history of variability of sources across the spectrum. So from using X-rays, gamma rays, and all the optical near infrared that we have, and use information about the friends of this transient to infer what the transient is. The beauty of this approach is that it's limited by the time that it takes to us to query everything, and but it's not limited. We don't have to wait for the next data point in our light curve. And thankfully here we are helped out a lot by the physics of transients. that like or don't like some environments. And this approach will rely heavily on photoz's in the local universe, which is a true challenge. I'm sure any of you that try to do photoz's at redshift below 0.1 knows that very, very clearly. The beauty is that the transients know where they're born, they know their friends. So we can infer something about the transients just looking at where they're born. And we can infer something about the transient based on where from their host. All of this relies on one piece of information that is a reliable host galaxy identification that seems very, very easy to associate a transient sometimes to a galaxy, but some other times the transients really are nasty, and even a reliable host galaxy identification is actually a non-trivial process when you don't even know what is a galaxy at large distances. So what we would like, the dream in the era of the LSST is really to have an engine instead of a robot, instead of humans that actually take the decision and tell us, yes, now you can repoint your very expensive spectroscopic follow-up or X-ray radio follow-up to this transient because you have a lot of potential to make a discovery. That's the dream. So the message here is that I think that in the next 10 years, we will have to work hand in hand with computing scientists, software engineers, and abandon more and more the idea of being, of having the grad students coming up with some software and find an ad hoc solution to each little problem. So going back to these two parts of the territory that I would like, I think that there are very, very rich of discovery power, fast transients, and counterparts of gravitational waves. So what can we do with LSST? And fast transients, just here is the same slide as before. Look at how terrible is the coverage, the temporal coverage of LSST. And so let's forget about my way of thinking is that, okay, forget about the fast transients in the wide deep fast. We just need to use another solution. And this might be a mini survey, a mini LSST survey, or it might be a completely different survey. And here is one slide of advertisement of a new survey, the LaCie-Schmidt Southern Survey, LS4 in short. We got tentative approval by ESO a few days ago. PI Peter Nugent is in LaCie, as the name says, and the quick quick fact is that it's a wide field survey is going to complement LSST in depth. So when LSST is going to saturate, this is not going to saturate, and in cadence, of course. And what I personally particularly like is that differently from many surveys out there, we are committed to make 90% of data or more public immediately. So it's going to be a resource for everybody, and it's going to be in the right location to complement LSST. So stay tuned. A lot of institutions, UK institutions are our partners, and some are part of the executive committee. So it's glad to have all of you on board. So, okay, and that's my way to solve the problem of the fast transients. So basically abandon LSST and try to instead use other data to complement LSST. What can we do with gravitational wave counterparts instead? So here is our 170817 kilonova with data collected by worldwide effort. So what is the future after 170817? And I try to list here the places where I believe are the frontier after 170817. And without going through each single bullet, those frontiers can be reached only and only if we can go deep, because intrinsically these transients are faint. That's the key reason. And second, they are fast evolving, so we need to do to get on target fast. So fast and deep is what we want. And the reason why we want the Rubin Observatory to play a role here is because of the depth that LSST can give us. So here I created some kilonova light curves, and you can see those kilonova light curves in the 6 LSST filters. And I created those light curves with different ejecta mass just to get a feeling of the potential variety. of these Eclairs. And what I want to bring home is that since the gravitational wave instrumentation, the sensitivity scales like 1 over distance, but instead in the EM world, the sensitivity scales like 1 over distance squared. That means that we will be very easily outpaced by the gravitational wave world, and we really need to use the big glasses to try and find all the counterparts to these gravitational wave sources. So here I'm using 100 megaparsecs and 200 megaparsecs. If you go to 200 megaparsecs, you can really see that LSST, potentially with a longer exposure than, or maybe multiple exposures, not just one exposure, than the typical visit is what we need. So we need depth. That's a message that I wanted to convey. So, why I heard a lot of times people tell me, well, we're gonna cover that area of the sky anyway, so why we can just rely on luck, and at some point that field is going to be covered by LSST. Well, luck is not a good idea. I did some back of the envelope numbers, and we would have something like some percent probability to cover that part of the sky. And we would have very limited color information. So at the end, even if a counterpart is there in our observations, we might not be able to do the science. So my answer is that if we want to play the game of gravitational wave follow-up with LSST, we need target of opportunities. And that's the way to make the best of this data. Another comment that I get is why we can't just do galaxy targeted searches that were so powerful for 170817. The answer is very obvious. It's when we increase the distance, we don't even know where the galaxies are. So it's not a good idea for that reason. Instead, what we proposed in fall 2018, and a lot of you were part of this effort, was to try to convince the project to have a target of opportunities. And we have been selected by the SAC for implementation in the LSST simulations that they are doing right now. And I'm in contact with Zelko and his team to try and understand which kind of success we can hope to have with the strategy that we propose. Just to give you a feeling of what we propose for, remember 90% of the time LSST goes into the main survey, and then there is 5% or more in the drilling field. So there's going to be 2% in the mini surveys. All this left is effectively a few percent, and that's what we asked for. We put out a minimal strategy for follow-up that if you scroll down in the last bottom of this table, we were requesting 1% of LSST time, but our optimal strategy that would allow us to actually do some experiments of following up black holes, so some unidentified gravitational wave sources, would bring us to the 2.3% of LSST time, and that's what I'm trying to push for. So last point, I know I'm probably running too late, so I just want to make one point, and my laptop conveniently froze. So yeah, so one point is very close to my heart is that LSST can actually, the data can be absolutely enhanced by triggering observations across the spectrum. And in my mind, so the way we have been playing the game until now is mostly by getting the trigger from one facility and repointing all the others, so leaving all the others to one. And what I do believe is a very beautiful opportunity for the future will be to evolve from follow-up into co-observing. So having multiple observatories that reach an agreement to observe that patch of the sky at the same time across the spectrum. I do believe that would enable a lot of science, and that's all I have for you. Thank you.
Thank you very much, Rafaela. Neil, do we have any questions?
No, we don't.
Maybe I could ask one. Rafaela, so your last slide, you talked about co-observing. Is this a rapid response mode co-observing, or just co-observing in the hope that something occurs in their field of view?
Yeah, so my dream would be to have wide field of view observatories looking at the same patch of the sky, at least for some portion of the time. And
slaved observing.
Yeah, yeah. So you rely on the lack of having something happening there, but you don't have to repoint, so you could get that snapshot of the spectrum at the same time.
That's an ambition.
It is. It sounds great to me. Right. Okay.
Do we have any other questions?
It doesn't look like it. Oops.
Okay. In that case, thank you very much, Rafaela, for that very full talk. Obviously, a lot of interesting stuff going on and about to become very real. So we now have a 15-minute, well, slightly less discussion window. Paul, did you anticipate leading this?
I can do, I suppose. The idea was just to leave some time in case people have overall questions or overall suggestions, particularly from the younger members of the listening audience who may not have asked anything before. I realise you've got to use the Q&A, which inhibits things a bit. And it's interesting, we've got all these facilities coming. They have slightly different, one topic is they have slightly different ways of handling the public access to data. LSST being an example in kind, where there are opportunities to join, but what happens if you haven't joined, and so on. SPOM has its own policy, SWIFT has one, of course. So is this disjointed approach to public access going to inhibit the field or not? People have to, of course, pay for their facilities. So countries want to get, or agencies want to get a payback for their community. But is it a good thing to have not everything public? Anyone have a view on that?
Am I right in thinking that Thesis data is planned to be public?
That's our proposal to ESA, yeah.
Right.
It's up to them, of course, but they seem to be, well, both agencies, NASA and ESA, are moving in that direction for future missions. Well, as public as possible is the phrase they say, whatever that means. But yeah, we'd want it public.
Whilst people are pondering that, I had a question for Sheila, actually. I don't know if Sheila's able to unmute. So you talked about the next generation, the Cosmic Explorer and Einstein telescope. Are we anticipating one of each or multiple instances of both types, or how do you see that? Because I'm thinking about the location capability. That's what's concerning me.
So there's been quite a bit of work actually done on the question of how well you can locate with a number of instruments, and there are some papers. Again, I can point to you on that. And actually, again, you can do reasonably well without a network, but as you might guess, the more you have, the better it is. But also keeping some of the second generation going also can help further with that particular question. I mean, currently the vision is for one Einstein telescope, but actually within the instrument there are multiple interferometers. So it's within the one observatory facility there are multiple interferometers. With Cosmic Explorer, I mean, there's an open question. Again, Cosmic Explorer is at the design study stage. All of these things are being looked at in terms of what constitutes an optimum network. You could see that little shaded L in Australia, again, on one of the last plots that I showed, because there was some interesting work done a while ago. Again, I think, I'm not sure if Martin Hendry's actually still on the call here, but looking at this question of what is the optimum distribution of detectors on the surface of the Earth? And even if you start with what you have or you start from a blank sheet, Australia always turns out to be a good place to have one.
Martin is on the call, so if I let him speak, he can try and let him. Oh no, sorry, he's not.
He's maybe dropped off. But I can. There's a nice paper actually looking specifically at what the capabilities are with different numbers of instruments in different locations on the Earth.
Actually, no, Martin is on, so you can try and speak, Martin, if you want.
Oh, there's an anonymous attendee. I'm not sure if that's relevant to this question or a previous one. Who's asking if they can speak?
Anonymous attendee. I'm not seeing that.
Oh, it's Susanna V.
Anyway, there are some questions in the Q&A.
So I'm not going to quantify it for you because it's not. It's a more complicated question in terms of exactly where the combinations and permutations of where you might put instruments. But I can certainly send you a link to the paper that actually looks at that.
I don't want to ask all the questions, but I do have quite a few. So one question is, are the SFOM and Einstein probe teams talking to each other regularly? Because they're both going to be flying at the same time. It would be good to have efficient cooperation there. I don't know if Wymin wants or Damien wants to talk about that.
Hi, Julian. Yes, the answer is actually we start to talk to the SWARM team based on a program established by the CAS, actually will be funded to study how the two missions can do synergy together, whether we choose to point into the same direction or just the opposite phase. It's pointing to opposite phase. Actually, the good thing is that putting the two observatories together, we will cover a very wide spectral range from the optical all the way to the gamma rays. And we have different capabilities in terms of finding transients and follow-up observations. So this is a very interesting topic. Actually, we start to think about it. And I believe we will have a synergy in the future.
Does China have a mission or missions concept beyond Einstein probe? I mean, there's EXTP, I suppose, but is there any longer term view than that?
There are several mission concepts regarding the high energy in the X-ray band. EXTP will be the one. Of course, there are other mission concepts like exoplanets and other things.
Yeah, okay. We're running out of questions. Any of our attendees have anything they want to ask? I think you can stick your hand up if you wish. Everyone's been very shy on a Friday afternoon.
Susanna Vegani has put a question in the Q&A.
Oh. So just a comment about localization and science with Einstein telescope. America presented simulations on ET and Advanced LIGO Virgo Cagra working together, showing great potential. Are the funding agencies likely to keep both 2G and 3G funded at the same time? That's a good question. I guess that's a question for you, Sheila.
Well, that's a question for the funding agencies, but in terms of the science, I think there's been, something I should have said during the talk was obviously we've been talking about, you know, activities in Europe, activities in the US, possible thing in Australia. That's all coordinated by GWIC, the Gravitational Waves International Committee, which is the body that essentially has the heads of the international laboratories on it. It's an official IUPAC working group. And it, again, if you type GWIC into Google, it'll take you to the GWIC webpage. And so GWIC has, over the last few years, had a series of working groups looking at these specific questions, again, like Julian's question. And so that's where quite a lot of this work has come from. And I think the work that Susanna is talking about is part of that. It has looked at these issues. How many detectors? Where should the detectors be? Do you gain from having 2G and 3G detectors running together? What are the trade-offs? So as I say, Google is your friend. If you Google,
I assume if you're not upgrading the facilities, the 2G, the actual annual running costs are not extraordinarily high, I presume, because if you weren't, you know, doing anything to them, as we do with smaller telescopes, of course, we don't shut them all down as we build bigger ones. It's not exactly the same, but given the third generation are not in the same physical place, there's no reason why you couldn't keep them running, presumably.
I think that's right, and as ever, it will be as it is with all these instruments. It's a question of science return. You know, it's a cost benefit. At what point does the cost of keeping something running outweigh the science delivery? But I think certainly in the first instance, you know, one can see. I mean, we're still at the point where, as I mentioned, we're still in discovery phase with the first generation. This is a very long-term plan to look to the 2030s and 40s. So, you know, it's quite hard to prejudge what will happen between now and then.
And having a gap due to money is different to having a gap due to upgrades. So
yeah.
It'd be great if they keep going. Yeah. Okay, well, we're in the last couple of minutes. So again, just I don't think there are any new questions. I hope that answered Susanna's questions. So I'd just like to thank our speakers, particularly those in strange time zones. So Raffaella was having breakfast, or Wyman was having dinner, and the rest of us had lunch, hopefully. We'll try and collect together the talks. I'm not sure what we'll do with them since there isn't an RES page, but we'll think of some way of distributing maybe. It's always nice to have these things. So I hope everyone keeps safe and we can get back together at some point, either the AAS or an RES meeting, maybe this time next year or something like that. It's a depressing thought. But again, thanks to everyone and thanks to those for listening. We had about 70, 80 people pitching up, which isn't bad for a Friday afternoon. So keep safe and have a good weekend, everyone. So bye.
Thank you, Paul. Bye.
Bye,
Bye everybody.
My hand's disappeared. There it is.
Bye-bye.
Bye-bye.